Yes, yes. Am I audible to everyone?
Yes, sir.
Yes, sir.
Yeah, we'll start. Okay. Screen is visible, right? So last class, I think we ended on that hemoglobin part, right? From then onwards, only we have to continue. Hmm. So this is where we ended, right? Now we have to move from here, and then we'll start with S block. Okay. So the next important compound of carbon was carbon dioxide. Okay, and how do you prepare carbon dioxide? So you can see it can be prepared by complete combustion of carbon. So if you do incomplete combustion means what? In limited presence of oxygen, you will get carbon monoxide. But if complete combustion, that is excess of oxygen is taken, in that case, we are going to end up with what? We are going to end up with carbon dioxide. Is that clear? Not just that, you can also you can also do combustion of any hydrocarbon. CXHY is what? Hydrocarbon. It will give you CO2 and H2O. So that is also one of the preparation of carbon dioxide. But in laboratory, how do we do this? So in laboratory, how do we prepare this? So we treat calcium carbonate. We treat calcium carbonate with what? Dilute HCl. So when we treat calcium carbonate with dilute HCl, we end up with all this product and CO2 gas is also there. Is that clear? So this is also the one of the preparation method. And this is laboratory preparation method. Is that clear? Now in commercial scale means what? Industrial purpose. Commercial scale means what? Industrial purpose. How do we prepare it? So we just heat the limestone. Calcium carbonate is nothing but limestone. So on heating the limestone, it undergoes thermal decomposition and it results in formation of calcium oxide and carbon dioxide. Is that clear? So these three methods of preparation are there for carbon dioxide. First one is what? Complete combustion. Okay. Then second is the other two methods involves calcium carbonate. One is thermal decomposition of calcium carbonate, and the other one is what? Treating of calcium carbonate with dilute HCl. What do we end up with? Calcium chloride, water, and CO2. Now, now what about the properties? So it is odorless gas, it's a colorless gas, and it has low solubility in water. Okay. And the nature of the oxide is acidic in nature. We have studied, no, CO2 is acidic. CO2, SiO2, and GeO2, they are all acidic in nature. We have studied it in last class. Okay.
Sir, could you show the first slide 1 second?
First slide. Done?
Yes, sir.
Okay. Now, so now, low solubility of in water. Okay, carbon dioxide is low soluble in water. So it's low solubility in water. It makes of immense biochemical and geochemical importance. With water, it forms carbonic acid, which is a weak diabasic acid and dissociates into two steps. We all know that carbonic acid is nothing but H2O plus CO2. Is that clear? So H2CO3 is a weak acid and it's a diprotic acid. And factor is 2. So in first step it will dissociate one H plus and second step also it will dissociate one H plus. And this buffer H2CO3 and bicarbonate buffer is it's a buffer which maintains the pH of blood. Okay. So this is also one of the properties that the carbonic acid and buffer the bicarbonate buffer which is formed it regulates the pH of blood. In ionic equilibrium, you would have discussed this. Yes or no? Do you remember this? And in a solution chapter in the upcoming physical chemistry part, you will study Henry's law. So you see all these carbonated soft drinks, right? What is it? It is nothing but pressurized CO2 which is dissolved in water. And when you open the cap of the bottle, slowly the gas fizzes out, right? Therefore, you can see the fizz in when you pour the drink in the glass. You can see that fizz. So why that fizz takes place? Because the carbon dioxide gas, which is heavily pressurized to get dissolved in water, is now because of difference in pressure, it will be liberated or it will be released. What one more application of CO2 is what? It is one of the key players in doing photosynthesis. Yes or no? You can see the reaction CO2. So what do plants do? The plants, they take the carbon dioxide and with the help of chlorophyll, they convert it in glucose and oxygen is released. So oxygen is important for us, CO2 is important for plants. Is that clear? And with the help of chlorophyll pigment, they perform the photosynthesis, and this is the overall reaction for photosynthesis. Glucose will be produced as their food, and oxygen gas will be released for us humans. Is that clear? Yes or no? So this is just a quick, or you can say a visual representation of how photosynthesis would look. So energy is given, carbon dioxide is there. Plants will take that carbon dioxide, it will convert it into this glucose and oxygen. Okay. Unlike carbon monoxide, CO2 is not poisonous. I told you that case, right? In colder regions, people, they when they used to off their windows and doors, and still that angithi was on. In that case, what is to happen? Uh, Carbon monoxide was forming eventually, and it leads to like fatal cases. In some of the region, it has led to some fatal cases. Why? Because limited supply of oxygen would be there. So whatever oxygen is there, that once it gets consumed, then carbon monoxide will be in excess. No, and carbon monoxide, because it is fatal or it is poisonous, so it can make the humans, dead. But CO2 is not like that. CO2 does not have that case. It is not poisonous. Okay. And increased level of carbon dioxide in atmosphere causes greenhouse effect, which raises the temperature of the atmosphere, which might have serious consequences. Therefore, all this delegation and all was there like 2 years ago to control the greenhouse effect, which eventually can't be controlled. CO2 emission will take place. There are so many works going on. And CO2 emission is something which we can, you know, try to decrease, but it will take place eventually. CO2 will be emitted in majority of cases or majority of the process which are there. CO2 is released. But anyway, one of the effect of CO2 is what it hampers the greenhouse gases. Okay, it causes a greenhouse effect, and because of such cases, what happens then? Depletion of ozone and all will take place. So it has a natural consequences. Now, CO2 molecule. So we all know it's a sp नहीं, it is sp2 habitats, no? No, no, sorry, my bad. It's sp only, yeah, double bond. See, sigma and pi. So you only consider the sigma bonds. We don't consider the pi bonds. So carbon has two sigma bonds, therefore it is sp habitats. We all know that. This is just a molecular orbital, like chemical bonding part, which we are not going to discuss too much. I'll just read it quickly. So two sp habitats orbitals of carbon atom overlap with two p orbitals of oxygen atom to make two sigma bonds. We can see this one sigma bond and two sigma bond. So carbon is hybridized, and the hybridized orbital of carbon is nothing but sp orbital. So that sp hybridized orbital of carbon will overlap with p orbital of oxygen atom. Is that clear? And that is how two sigma bond will form. This sigma bond is formed by overlap of sp orbital and p orbital. This is also formed by overlap of sp orbital and p orbital. Is that clear? To make two sigma bond. While other two electrons of carbon atom are involved in p-pi bonding with oxygen atom. You can see this pi-pi bond. So this is the p-pi bond which we are talking about. This results in linear shape with both carbon oxygen bonds of equal length. What is the bond length? 115 picometer. And there is no dipole moment. Why? Because the dipole gets cancelled. No. So this is here and then this will move here. So this always, what is the flow of dipole? Less electronegative to more. So carbon is less, oxygen is more electronegative. So it will flow like this. Okay, and one dipole will be in this direction. So both the dipoles are cancelling out each other. As a result, the overall molecule is non-polar, and it's a like it does not, because the dipole moment is zero in this case. Okay, these are the Lewis dot representation of resonating structure of carbon dioxide. Moving on. Carbon dioxide can be obtained as solid in the form of dry ice by allowing the liquefied CO2 to expand rapidly. Dry ice is used as refrigerant for ice cream and frozen food. See, you would have seen this Amul ice cream and all having pan India, right? But the plant of Amul, it's in Anand. Anand is a place in Gujarat. Full form Amul is what? Anand Milk Union Limited. So from Anand, a place in Gujarat, they have to, supply or transport the ice creams pan India, how would they do? Won't the ice cream be melted in the way? So what do? They use solid CO2. What do they use? Use solid CO2, which is also called as dry ice. And because dry ice is a very good refrigerant, it can it makes sure that the ice cream does not melt before reaching the respective stores. Exactly. So this is one of the application of carbon dioxide. And you also know that carbon dioxide is present in the fire extinguisher as well. You've seen these fire extinguishers, right? Kept close to lifts and all in the apartments. So gaseous CO2 is extensively used to carbonate softening. That is one of the applications that we already discussed. Being heavy and non-supportive combustion, it is used as fire extinguisher. Okay, a substantial amount of CO2 is used to manufacture urea. That is also one of the case. So application of CO2, what are the application or where the use of CO2 can be seen? So when CO2 is present in solid form, it can be used as dry ice and it acts as a refrigerant. Okay, and it is used to transport ice creams and other frozen foods so that they don't get deteriorated. And what about gaseous CO2? So gaseous CO2 has multiple application. It is used in fire extinguisher because it's a non-supporter of combustion, and a substantial amount is also used in manufacturing of urea. And gaseous CO2, even though it is less soluble in water, but with the help of pressurized machine, we can you know dissolve this CO2 gas in water and make carbonated soft drinks from this. Now, if you remember in last class, we studied two types of gases, water gas and producer gas. What is the difference? Water gas was a mixture of carbon monoxide and hydrogen, whereas producer gas was a mixture of carbon monoxide and nitrogen. But what was the difference? One more difference was there. The difference was in their molar ratio. What was the difference? The difference was in their molar ratio. Water gas was present in which ratio? 1 is to 1 or 1 is to 2?
1:1.
1 is to 1. Whereas producer gas was present in which ratio? 1 is to 2. And we are talking about molar ratio. So in this case, they are asking water gas is produced by. How do we get water gas? First option says passing steam through red hot coke bed. So do you believe it is correct? Yes or no? It's correct. No.
Yes, sir.
Red hot coke bed. So coke means what? Carbon is there, and steam. Steam means water, H2O gas. So and if you check for the other option, saturating hydrogen with moisture. So H2 plus H2O, liquid, wrong. Mixing oxygen and hydrogen in the ratio of 1 is to 2, that is also wrong. Heating a mixture of CO2 and CH4 in petroleum refinery, that is also wrong. Okay. Now we have to see compounds of silicon. Okay. So silicon dioxide is the first compound that we have to study. Okay. And 95% of Earth's crust is made up of silica and silicates. Silicon dioxide, commonly known as silica, occurs in several crystallographic forms. So these are the crystallographic forms in which we can obtain silica or silicates. Is that clear? So one of the crystal that we are going to get is quartz, then cristobalite is there, and then tridymite is there. So quartz is the most famous among all, but please remember the other two names as well, cristobalite and tridymite. Okay. The forms given above are some of the crystalline form of silica, and they are interconvertible at suitable temperatures. So this is also a very important point. The forms is quartz, cristobalite, and tridymite. They are interconvertible at a suitable temperature. Okay. Now, if we consider silicon dioxide, this is how the bonding looks like. Can you see as a silicon atom? If you see this silicon, one, two, three, four, five, six, seven, eight. Total eight-membered ring-like structure is there. Can you see this? Just go through the points. So silicon dioxide is a covalent three-dimensional network. This is all the three-dimensional network. Okay, solid in which each silicon atom is covalently bonded in a tetrahedral manner. A silicon atom is covalently bonded. Can you see? A silicon atom is covalently bonded in tetrahedral. Tetrahedral means what? There are four bonds. One, two, three, four. Is कहाँ गया? हाँ. Each silicon atom is covalently bonded in a tetrahedral manner to four oxygen atoms. Each oxygen atom in turn covalently bonded to another silicon atom as shown in diagram. So one oxygen atom, because oxygen valence is 2, no, so it will have two bonds, one here, one there. So all the oxygen atoms are attached to two silicon atoms. They are attached to two silicon atoms, and silicon is attached to four oxygen atoms. Is that clear? Each oxygen atom in turn is bonded to another silicon as shown in diagram. Each corner is shared with another tetrahedron. The entire crystal may be considered as giant molecule in which eight member rings are formed with alternate silicon and oxygen atoms. Can you see silicon, oxygen, silicon, oxygen, silicon, oxygen, silicon, oxygen. And this is a eight membered ring-like structure. Is that clear? So this is the structure or the three-dimensional representation of silicon dioxide. Now, coming to the application part. So, quartz is extensively used as piezoelectric material. Now, what is piezoelectric material? So, it is written over here. It has made possible to develop extremely accurate clocks, modern radio and television broadcasting, and mobile radio communication. So, the material which are used for manufacturing of all these units, the clocks, radio, and television, such materials are classified as piezoelectric material. Okay. And you would have seen those watches which have very high cost. So why do they have very high cost? Because एक तो उसमें अलग अलग दुनिया भर के चोचले रहते हैं. They will say that handmade, this, that. But one of the material is quartz also. So the use of quartz when the artist who makes the watch they do so they do modification in quartz as well. So that is also one of the reason why the pricing of watches vary according to the material. Okay. So quartz is there. Then silica gel. You would have seen those bottles in DMart and all. If you purchase something from DMart, they have this silica gel inside. This sachet is there inside the bottles and all. Why? Because this is nothing but a drying agent. It is nothing but a drying agent. So it prevents moisture inside the bottle and all. Okay. So you would have seen such silica gel sachet in containers in DMarts and any other shopping, retail shops. So, silica gel is used as a drying agent and as a support for chromatographic materials and catalysts. Now, what are chromatographic materials? Do you know? Chromatography is a technique to separate. So there are
Pigments.
there are different chromatographic techniques. So if you go for paper chromatography, it can separate pigments. Then if you go for column chromatography, it can separate compounds as well. Okay. Now this is the most important application. Okay. What is written over here? Kiesel good. What do we call it? We call it Kiesel good. It's an amorphous form of silica and it is used in filtration plants. Okay. So this is the most important application of the silica. Please remember, it is called as Kiesel good. Okay. And it's an amorphous form of silica. And generally it is used in which areas? It is used in filtration plants. In silicon dioxide, each silicon atom is surrounded by four oxygen atoms, and each oxygen atom is bonded to two silicon atoms. Correct or incorrect?
Correct.
First point is correct or incorrect.
Correct.
Each silicon atom is surrounded by four oxygen atoms. This is correct only. And each oxygen atom is bonded to two silicon atoms. This is also correct. So it means the first option is only correct or not? Yes, it is. Check for second option. Each silicon atom is surrounded by two oxygen atoms, and each oxygen atom is bonded to two silicon atoms. So the second statement is correct, but the first statement in option B is incorrect. Right? Option C. Silicon atom is bonded to two oxygen atoms. Wrong. These are double bonds between silicon and oxygen atom. That is also wrong. So option A is correct option. You can see the structure. The amorphous form of silica is just now we studied. The amorphous form of silica is Kieselguhr, and it is used in filtration plants. Where is it used? It is used in filtration plants. Okay. Now, other compound of silica is silicones. So, these are a group of organosilicon polymers. Now, what is organosilicon? So, along with silica, we also have carbon in that. So, carbon is represented by R, the alkyl body framework. R is nothing but it is representing alkyl framework. Okay, so these are a group of organosilicon polymers which have R2SiO as a repeating unit. Okay, so this is the repeating unit for silicones. And R here represents carbon framework. Okay, therefore it is called as organosilicon polymers. The starting materials for the manufacture of silicones are alkyl or aryl substituted silicon chlorides. So see the molecular formula. What is the molecular formula? RnSiCl 4 minus N. So if N is 1, then how much chlorine will be used? 3.
3.
If N is 4, then what about chlorine? 0, no? 4 minus 4. So obviously it won't be possible. So the starting material for the manufacturing of silicones are what? Alkyl or aryl substituted silicon chlorides. So SiCl is there, and obviously, see, silicon will have four bonds. No, it like, belongs to carbon family only, so it will form four bonds. So chlorine is monovalent, so four chlorine will be required. But if you substitute one of the chlorine by R, then whatever number of chlorines are substituted, that much chlorine will decrease over here, and that much R will be here. Therefore, this is the formula of what the starting material, that is alkyl or aryl substituted silicon chlorides. Okay. And what is the repeating unit? R2SiO. This is the repeating unit of silicones. So if I see this reaction, so CS3Cl, this is Rx plus Si in presence of copper powder at 570 at 570 Kelvin. So these are the different methyl substituted chlorosilane. Now, here only one substitution is done. Here, substitution is done twice. Here, substitution is done thrice. And then here, all the four, like all the four valencies are substituted. All the four valencies are substituted. Okay. So, acha, do you know NMR? Have you heard of NMR? No? ठीक है कोई बात नहीं or if we go on discussing, we have to discuss too much. I would have told you what this what is the use of this silanes, no? Chlorosilane, the general silane, this tetramethyl silane. It's used as a fuel in NMR. NMR is a machine, okay? It's a spectroscopic machine. So this tetramethyl silane is used as a fuel in there. Okay.
So could you go to two slides before?
This one or before this?
Before.
Before this one.
Yes, sir. One second.
Hmm.
Yes, sir. Done.
Oh, this is also done.
Yes, sir.
Done. Now, if silicones, like so if we have dimethyl dichlorosilane, so two methyl group and two chlorine, okay. So if it undergoes hydrolysis, then what will happen? So OH will, like H2 will come and attack on silicon because this is polar like del plus, del minus. So OH will come and attack. Then oxygen will be losing one hydrogen to remove the deprotonation. You know, na, this oxygen has lone pair. It will go and attack on silicon, whatever you study in organic chemistry. So H2 will attack, but oxygen will develop positive charge because it would have formed three bonds. No, so to remove that positive charge, it undergoes deprotonation. So it will lose H plus. So Cl minus and H plus will combine with each other to form HCl. And that is how you get this. That is how you replace this Cl by OH. Is that clear? So hydrolysis of dimethyl dichlorosilane, which is this compound, followed by condensation polymerization yields straight chain polymers. So that further step, I think it's given over here. Yeah. So you have got this compound. Now, when this undergoes condensation polymerization, what is condensation polymerization? You will study all of this in polymers chemistry. Okay. Polymers chapter is also there for advanced syllabus. But as of now, you know, condensation means what? Molecules will be condensed with each other. So for condensation to take place, some groups has to be removed so that the two molecules might be attached with each other. You can see it over here. So water molecule will be gone. OH and H is gone, so OSI bond will be there. Here also OH and H will be gone, so OSI bond will be there. Therefore, after polymerization, what will happen? SiMe and this O, and this is as it is. So this is the repeating unit that you're going to end up with. Is that clear? So on condensation polymerization, we end up with this particular part. And what is it? This is a straight chain polymer. Okay. Again, read the point. So hydrolysis of dimethyl dichlorosilane. Dimethyl dichlorosilane. First, what will happen? Both the chlorine will be replaced by OH. And now once we get this monomer, it undergoes condensation polymerization. So multiple molecules will be there. They will be, undergoing polymerization and at the same time condensation polymerization. What do I mean by condensation polymerization? So some of the groups will be removed and they will condense with each other. So this three will like this and this. They will be attached with each other. And you can see the representation. This is how we represent polymers. So instead of writing the same units again and again, we write it as polymer. What do we write? We write it as polymer. Okay. This N represents polymer here. Multiple unit it represents. The chain length of the polymer can be controlled by adding CH3 thrice SiCl. What would be the name? Hmm? Trimethyl chlorosilane. What is it? Three methyl group is there, na? Si is there, so silane it will be called as silane. And chlorine is also there, so trimethyl chlorosilane. The chain length of the polymer can be controlled by adding trimethyl chlorosilane, okay, which blocks the end as shown below. So what does it do? So this Cl, it will replace the Cl in this case by OH. If I have this thing, okay, condensation will take place. I can see this OH is there. After the reaction of this, when it undergoes hydrolysis, Cl will be replaced by OH that is there. Now, when we have this trimethyl wala part, okay, CH3 thrice SiOH, what will it do? So, CH3 thrice, can you see this? CH3, 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 and OH. And here we had that previous unit to because we have to block the chain length. No, so how to block the chain length? So what you have to do is you have to use this, because if you don't replace this the OH by methyl, this will go on continuously. No, so this chain will increase continuously, but we have to block the chain. You can see in this case, if this OH is replaced by methyl, then here condensation will not take place, right? Again, and the chain won't increase. But if you have OH on the right hand side continuously, then what will happen? Eventually, the chain length will increase and condensation polymerization will be continuous. Therefore, what do we do? To block the chain length, to block the chain length, or to control the length of the chain, what do we use? We use this trimethyl chlorosilane. First, it undergoes hydrolysis, and this Cl is replaced by OH. You can see that, right? And now this is used with the previous case. In previous case, we had this product. No, you can see dihydroxy dimethyl silane. Now, when we treat them with each other, so this OH and H will undergo condensation. So OSI bond will form. But here there is no OH for further condensation. Therefore, the chain length will stop like this. There won't be further polymerization. Is that clear? So what is the use of trimethyl chlorosilane? It controls it blocks the chain length. Okay, what does it do? It blocks the chain length, or it controls the length of the chain. Can we proceed? Have you noted this? Understood? Can we proceed, guys?
Yes.
Okay. Silicons being surrounded by non-polar alkyl groups are water repelling in nature. Obviously, we know because alkyl groups are what? They are organic compounds. Okay, non-covalent. Covalent. And water is what? Water we have covalent, but water is polar. No, this is non-polar. So because we know that like dissolves like, so non-polar and polar won't be dissolved in each other. As a result, silicons also they are insoluble in water. You can say water repelling in nature. They have, in general, high thermal stability, high dielectric strength, and resistance to oxidation and chemicals. So this is the property that makes it more versatile for using in different application parts. Is that clear? Therefore, you can see what are the uses. So they are used as sealant, greases, electrical insulators, and for waterproofing of fabrics. Okay, so these are the different uses. Now, what is the second use? Being biocompatible. Being what? Biocompatible. They are also used in surgical and cosmetic plants. What is biocompatible?
So it doesn't
Compatible,
hurt the
biocompatible.
skin and all.
Doesn't hurt the skin and all. Okay. And what is sealant? Sealant क्या होता है भाई? हम्म हमारे पिताजी बोलते थे सीलेंट. पता नहीं that was Hindi sealant. I think it would be that sealant only because it is water repellent, no? So ये जो दीवार वाल में gap में आते हैं, you have seen this, right? The cracks and all in the walls that arises. So you do this on putty and all, no? Why do we do this putty and all? You know this.
So
Mm,
wall becomes smooth and you can paint better.
yeah. So I think this is that sealant only. so that the cracks and all which are developed in the wall, you can use the silicone materials to fix that because it is sealant. Okay, like it is used to mm, mm, fill the cracks and all which is developed in walls. That this is what is sealant. Okay, by definition, if you know greases and all, you already know. So, what you have to like take from this part, first of all, alkyl groups are present with silicones and they are water repellent because they are non-covalent or non-polar. Sorry, non-polar, not non-covalent. They are non-polar and water is polar. So therefore, they are not soluble in each other. Hence, they are water repelling in nature. And as a result, at the same time, they have high thermal stability, high dielectric strength, and resistance to oxidation and chemicals, which makes them more versatile for using in different applications. And these are the applications that we have studied just now. Okay. Uh, Me2SiCl2 hydrolysis will produce. You know, both the Cl will be replaced by OH. So the correct answer will be Me2SiOH twice. Yes or no? Just now we checked this, no? So, and this undergoes what? Condensation polymerization, and it forms straight chain polymer. And to stop the polymerization, what do? We use trimethyl chlorosilane. Just now we did this, right? Correct statement among 1 to 4 regarding silicons are they are polymers with hydrophobic character. Yes or no? Water repellent means what? They are hydrophobic only. They are
Hmm.
biocompatible. Correct or not?
And
Just now we studied no,
Yes,
because they are
correct.
biocompatible. Hence, they are used in cosmetic, like surgical and cosmetic appliances. In general, they have high thermal stability and high dielectric strength. True or false? True only.
yes,
Usually, they are resistant to oxidation and used as greases. Oxidation, reduction, everything there is resistant on them. So, all four statements are correct. So, therefore, all of these. The straight chain polymer is formed by how do we form straight chain polymer? So, what do? Hydrolysis of CH3 twice SiCl2 followed by condensation polymerization. True or false? First option is only correct. You don't even need to go for the other options. Yes or no? Just now we studied this. No. Both the Cl will be replaced by OH. And uh, after that, it undergoes condensation polymerization. So OH and H will combine with each other. Water molecule will be removed. And oxygen and silicon will be directly attached with each other. Right? Silicon has strong tendency to form polymers like silicones. The chain length of silicon polymer can be controlled by adding. Ha. So because the like to block the chain length, what do? Which chemical we use?
sir.
Trimethyl
Option
chloro.
C,
Me,
chloroside.
Yeah, option C. Just now we have seen this all. Okay. Now the most important part because advanced में the question is mostly asked from the silicates part only. Okay. So silicon ka the important part is silicates only. Whatever question like till date the maximum number of question in advance or mains like uh, before it was there in mains no so is mostly asked from the silicates part only. Okay, so this is the most important part of silicon. So what are silicates? A large number of silicate minerals exist in nature. Some of the examples are this feldspar, zeolites, mica sheet, and asbestos sheet. Asbestos sheet you would have used in laboratory. Have you used in laboratory asbestos sheet?
Yes, sir.
Mica, you know where is mica used?
sure, electrical.
It's an electrical insulator, but good conductor of heat. So it is used. Where is it used? In iron प्रेस पता है ना हम लोग बोलते हैं ना प्रेस कर दो अरे दिस आयरन इज देयर नो आयरन करते हैं ना कपड़े को हम लोग प्रेस करते हैं सो दिस आयरन हैज मीका शीट्स राइट नहीं पता तुम लोगों को यू आर नॉट स्टडीड दिस मीका शीट एस्बेस्टोस इज यूज्ड इन laboratories चलो anyway so structural unit so it is what tetrahedral structure what is the structure tetrahedral structure so silicates are the basic unit of silicate is SiO4 4 minus in which silicon atom is bonded to four oxygen atoms in tetrahedral fashion you can see this each oxygen atom has minus one charge therefore overall charge is what minus 4 tetrahedral structure of SiO4 4 minus anion now what is the representation this is how the representation of SiO4 takes place. So this dotted circle represents silicon, whereas this represents oxygen. Where is the fourth oxygen, sir? अरे, it is tetrahedral. No. So ये fourth वाला इसके साथ overlap कर रहा होगा. There is one more oxygen atom which is going to overlap with this one. इसके नीचे ही है वो. Is that clear? Understood or not? This is the representation of silicate unit. And what is the silicate unit? It is SiO4, 4 minus anion. Okay. Yeah. In silicates, either the discrete unit is present or a number of such units are joined together via corner by sharing one, two, three, or four oxygen atom per silicate units. अभी ये सब क्या है? We are going to study this because of this only, because of different bonding structure, we are going to get different silicates. Okay, we'll study this further. When silicate units are linked together, they form chain, ring, sheet, or three-dimensional structure. So these are the types of silicate that you have to study. Negative charge on silicate structure is neutralized by positively charged metal ions. Two important man-made silicates are glass and cement. These are the silicates which are developed by humans, or we have prepared it. They are not naturally occurring silicates. Okay, glass and cement are not naturally occurring silicates. This is the silicate that is prepared by humans, or it is a laboratory prepared silicate. Okay, now what are all these points? Eventually, we'll study this. Like, as we are going to move with the silicates topic, we are going to study all whatever these points are mentioned over here. Okay. See, the first silicate is what? Orthosilicate, also called as nesosilicate. A wide variety of mineral contains discrete tetrahedral, that is, they share no corners. They have the formula. Acha, can you see this Roman 2? What does Roman 2 represent? The Roman number represents the
Two
charge.
charge.
What do they represent? They represent the charge on the metal. So metal is in plus 2, it means it is which metal? Group 2 metal, no? If metal is in plus 2, then it is which metal? Group 2 metal. Or the metal which shows plus 2 oxidation state. Is that clear? And we all know SiO4, what is the overall charge on SiO4? 4 minus. To balance this negative charge, total positive charge required will be how much? Plus 4, no? Then only the compound will become neutral. You understood my point? The charge on silicate is what? Minus 4. To balance out this charge, the positive charge also should be plus 4. Therefore, we have taken two metals which has plus 2 unit or plus 2 charge. So 2 into plus 2 will be plus 4 charge, and plus 4 will balance minus 4 charge. Is that clear? So if you see where M may be beta, manganese, so beryllium, magnesium, iron, manganese, or zinc. So these are the elements which are going to show plus 2 oxidation state. These are the elements which are going to show plus 2 oxidation state. Or instead of plus 2, if you have plus 4 showing iron, plus 4 showing metal, then directly use only one metal. And for that, the example is zirconium, Zr. For that, the example is what? Zirconium. Is that clear? So in orthosilicate, what you have studied? Tell me. Uh, the formula will be M2SiO4 or MSiO4. M2SiO4 means what? The metal will be in the plus 2 state, or if it is M4SiO4, sorry, MSiO4, it means what? The metal is in plus 4 oxidation state. Example is zirconium silicate. Okay. And the most important point is what? It is tetrahedral. The silicate unit is tetrahedral and they share no corners. They share no corner. It means they are not further attached with anything. Only this is present over there. Is that clear? Only this is present over there. No further connection is seen. Can you see? Is there any further connection? They share no corner. No, so corners are not shared. Is that clear? In which case, in case of orthosilicates. Next, pyrosilicates. You can see
Sir, could you show
ortho
the
में
previous slide? The
this
before
one
this one.
before this one.
Yeah, so 1 second.
Then
Yes.
okay. So just now the first point that we studied was in silicates, either the discrete unit is present or the silicate has the discrete unit, no, in which there is no sharing, the corners are not shared, or a number of such units are joined together via corners by sharing one, two, three, or four oxygen atoms per silicate unit. So the first one, the orthosilicate one, is the discrete unit one, in which there is no sharing of corner. Is that clear? That was the orthosilicate. But now, eventually, when we will move further, we'll see that silicates can be attached to each other via one, two, three, or four oxygen atoms. Is that clear? Chalo, moving on. So orthosilicate is done. Pyrosilicates, also called as sorosilicate or disilicates. Okay. So in this, two tetrahedral units are joined by sharing the oxygen at one center, thus giving the unit Si2O7. See, SiO4 was there, no, but here one oxygen atom is shared. Here one oxygen atom is shared between the two silicates. Can you see? This is one silicate unit and this is other silicate unit. They are attached to each other with the help of this common oxygen atom. So here one oxygen atom at the corner is shared. No, such silicates are classified as pyrosilicates. Such silicates are classified as pyrosilicates. Is that clear? An example of that is what? Orthobetite, which is what? Scandium silicate, scandium based silicate. Is that clear to everyone? Acha, what will be the overall charge? So you can see -1, -2, -3, -4. Okay. And then इसके नीचे भी एक सिलिक ऑक्सीजन is there, so -5, and इसके नीचे भी एक ऑक्सीजन है, which is what? -6. So I told you, no, the 3D representation. SiO4 is there actually. So one, two, three. Where is the fourth oxygen? It is beyond, beneath this. It is beneath this silicon. Okay, so this dotted represents silicon, and this circle represents the oxygen atom which is there. You can see this. The dot represents silicon, and the circle which encircles this dot represents oxygen atom. So total, how many oxygen atoms are there? Seven. One, two, three, four, five, six, seven. You understood this, right? So pyrosilicates में two silicates are joined to each other by share, and they share one oxygen atom. They share what? One oxygen atom. Example is what? Scandium base, and the name of this silicate is what? Orthowhitite. Orthowhitite. Whatever you want to call. Done. Noted. Pyrosilicate, orthosilicates understood. Orthosilicates, there is no sharing of the corners, but pyrosilicates में sharing takes place. Sorted. Can we proceed?
Yes, sir.
Okay. Cyclic silicates. If two oxygen atoms per tetrahedron are shared, ring structure may be formed of general formula SiO3 minus 2, and N means number of units. Rings contain 3, 4, 6, and 8 tetrahedral units are known, but those with 3 and 6 are the most common. देखो, this is one of the unit tetrahedron. This is one of the tetrahedron. This is also one of the tetrahedron. Total, how many tetrahedron are present in this case? Three tetrahedrons. Can you see this? Three tetrahedron are present. In this, one, two, three, four, five, six. So 3 and 6 one are the ones which occurs mostly. Is that clear? Rings containing 3, 4, 6, and 8 tetrahedral units are known, but those with 3 and 6 units are the most common. Are the most common. The Si6O8 minus 12 unit occur in beryl. So this is the silicate which exists. Emerald has the same formula as beryl except that it contains 1 to 2% chromium, which gives it a strong green color. This is just a data point of view. What you have to remember in cyclic silicate is the line. If two oxygen atoms per tetrahedron, can you see? This is the tetrahedron. This and this are shared. No. Similarly, for this tetrahedron, this and this are shared. So when in a tetrahedron, one oxygen atom is sharing, then it is called as pyrosilicate. If two are sharing, then it is called as cyclic silicates. And in cyclic silicates, the most common one are 3 and 6 one. The most common one are 3 and 6 tetrahedral units one. Is that clear? So we have tried to study total three silicates, ortho, pyro, and cyclic. Ortho mein there is no sharing. Pyro mein what is happening? One oxygen atom is shared between two tetrahedrons. to two tetrahedral units. Here in cyclic silicate, what is the case? Two oxygen atoms are shared per tetrahedron. Is that clear? So one tetrahedron unit will share two oxygen atoms, which we have seen already. So if I consider this tetrahedron unit, this one, it is sharing this and this one. No. So one tetrahedron units are sharing two oxygen atoms. Can you proceed? Cyclic silicate also done. Hmm. Hmm. Okay, let's see if in this case they have asked the charge on the silicate. What will be the charge? So how would you know? What will be the charge? See, aluminum shows plus 3, no? So 3 into plus 2 is what? Plus 6. And beryllium shows plus 2. 2 into plus 3 is what? Sorry, 3 into plus 2 is what? 6. So 6 plus 6 will be how much? 12. So if this is plus 12, then this will be minus 12, which you can see from here. You can see this, right? Can you proceed, guys? Cyclic silicates over. Now comes the chain silicate. Now comes what? Chain silicate. So simple chain silicates or pyroxenes are formed by sharing of the oxygen atom on two corners. Oxygen atoms on two corners of each so tetrahedron with other tetrahedra. Each tetrahedron with other tetrahedra. So if you see this, hmm, just say, hmm, simple chain silicates or pyroxenes are formed by sharing of the oxygen atoms on two corners of each tetrahedron with other tetrahedra. This gives the formula SiO3 minus 2. Okay. O3 minus 2 means this and this are shared. Okay. With two other different tetrahedrons. Okay. So if you see chain and cyclic are almost same only. But what is the difference? Cyclic mate is closed. Can you see this? A closed structure is there. Chain mate is not closed. Chain mate is open. That is one of the case. And whereas the technicality is same if you see. Both of them are sharing how many oxygen atoms? Two oxygen atoms. Both of them are sharing how many oxygen atoms? Two oxygen atoms. Is that clear? You can see this. This tetrahedron unit is sharing this oxygen and this oxygen. Similarly, this tetrahedron unit is sharing this oxygen and this oxygen. But what is the difference? This is an open structure, whereas in this case it is a cyclic, that is a closed structure. Is that clear? Tell me. Here also, if you see, then sharing of oxygen atoms on two corner of each tetrahedron. So one tetrahedron is sharing two oxygen atoms. In that case, also one tetrahedron was sharing two oxygen atoms. What is the difference? But the difference is this is open chain structure and that is closed chain structure. An example of chain silicate, what is the example? Spodumene. What is the example? Spodumene. SiO3 2 minus. SiO3 2 minus. This is the formula. This gives the formula of this is what SiO3 2 minus. Mm, just a minute. See, here also the formula is same only SiO3 2 minus, and here also the formula is same only SiO3 2 minus. Yeah. So if you see the technicality is almost same. The what is the difference? Both of them are going to share how many oxygen atoms? Tell me. Both of them are going to share two oxygen atoms, but the difference is what? Chain is an open structure and cyclic will be closed. Even their basic formula is same, SiO3 minus 2. There also it was SiO3 minus 2. Okay. So remember this difference total. We have studied total how many silicates? Four silicates. First one was ortho. Then comes after ortho, what we did? Pyro. right? Yes or no? Ortho, pyro, then cyclic. Pyro also called as pseudosilicates, disilicates, whatever it is. Let it be. Cyclic and then chain silicates. Moving on. Okay, so double chains can be formed when two simple chains are joined together by shared oxygen. When two simple chains are joined together by shared oxygen. These minerals are called amphiboles and they are well known. There are several ways of forming double chains giving formulae Si2O5 minus 2 and then Si4O11 and so on. Okay, this formula is not like we are not bothered about this. Now, what is it? Like how is it different than the previous one? So here, chains like the chains which are there, they are eventually resulting into the formation of cyclic structure. If you see, so double chains can be formed when two simple chains are joined together by shared oxygen. So if you see, this is one chain, this is one chain. If I take one more chain down only, can you see this? Just take it like this. Just इसको उल्टा कर दो. Whatever it is, no. This unit को if you make it ulta. So if you have this particular part and just flip it. If you just flip this particular part, what will you end up with? You will end up with this structure. You'll end up with this structure. So what they have written, double chains can be formed when two simple chains are joined together by shared oxygens. Two simple chains are joined together by shared oxygen. These minerals are called amphiboles and they are well known. So chains, amphiboles are nothing but chain silicates which are joined to each other, in which two chains are joined to each other. Such silicates are called as amphiboles as well. They are also called as amphiboles. Am I clear to everyone? Tell me. समझ में आया मैंने क्या कर दिया यहाँ पर? Hmm? So
हाँ
this
जी
was one chain. This is one chain. If you flip this chain and if you join together, if you join both the chains together by a common oxygen or a shared oxygen like this, is that clear? Then we end up with chain silicate only, but double chain silicate. It is double chain silicate. Is that clear? So chain silicate mein, if there can be only one chain, okay, that is normal chain silicate. But if you take one more flipped chain of this only, and if you join together by common oxygen or shared oxygen atom, you'll end up being amphiboles. What it will be called as, this mineral will be called as amphibole. Is that clear? Tell me. Now, if we count the number of this Si4O11, so count the number of oxygen, sorry, silly atoms. So 1, 2, 3, 4, 5, 6, 7, 10. ये कौन सा वाला ले रखा है इसने फॉर्मूला तो ये दिया है इसने Si4O11 6 and 2, 3, 4, 5, 7. Okay. Mm, 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 sorry, 3, 11, so 4, 3, 7. Okay, so 1, 2, 3, 4. We just count up 4, 5, 6, 7, 8, 9, 10, 16. Hmm, 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 हाँ, no. Uh, इसका फॉर्मूला में क्या गड़बड़ है कुछ? Because the formula is not matching. There are several ways
sir
of
I think it's
doing it.
taking smallest unit, so if you like split the ring into half, so if you place that ring again it will repeat over there. I think it's
Mhm.
taking it like that.
What?
Sir,
Repeat
if you
it.
take like the topmost silicon atom
The
and
top.
break the bond just next to it, like all the bonds just next to it, and all the bonds just next to the bottom silicon atom. So if you place that structure again and again and again, you'll get the ring.
हम्म, नहीं समझ में आया so you are there right what you said
Yes, sir. If you break the all the bonds next to, suppose all the bonds on to the right of the topmost silicon atom.
on the right to the topmost silicon this one you are saying this
Yeah,
one
जैसे अगर तो left वाला ring लिया and You
left,
break
this side,
all the bonds to the right of the topmost silicon atom.
is right of topmost silicon. You
So the
break all these
oxygen
bonds.
is
This
left.
bond. Okay.
And
So
so you do the same for the bottom one, you'll get like a C shape, and if you place the C thing again and again, you'll get the.
this Si4O11 still not come, no?
Yeah, so that will be in the C shape. Like if you take four silicon atoms clockwise, like from the top to the bottom.
मैं समझ नहीं पा रहा what you're trying to say. ठीक है चलो I'll see this. इसका मैं देखता हूँ. What you said is like you have to break the top right one, right? This is the top right one.
So I was saying like if you take the left valley ring,
Left ring, this side.
yeah, and the topmost silicon atom is there. If you break
This is
the
silicon.
right oxygen carbon,
This right oxygen. This wala
yeah,
bond.
yeah, if you
Okay.
break that bond and you break the
This bond.
same right bond for the bottom silicon also.
Right bond for the bottom silicon. Bottom silicon is this one.
Yeah,
Okay.
so
Okay. So
you'll
one,
get that
two,
C
three,
shape,
four.
no, 1, 2, 3, 4. And
Okay.
if you
One,
place
two,
this whole
three,
structure
four.
again, you're getting the left part of the next string. So that is repeating like that.
Okay. One, two, three, four. So if I count that oxygen, how many oxygens will be there? One, two, three, four, five, six, seven, eight, nine, 10. But oxygen atoms तो फिर भी नहीं सेम आएगा if you check. If you break this bond, let's say, so one, two, three. Three
Yes,
oxygen
yes.
atom is here. Then four, five, six, seven, eight, nine.
And then left.
Yeah. And then 10, 11. No, no, it's correct, correct. सही हो. Good, good. ठीक है. Hmm. Hmm. Okay. Cool. ठीक है. Moving on. Sheet silicates. So in sheet silicates, when SiO4 unit shared three corners, the structure formed is an infinite two-dimensional sheet of the empirical formula SiO2 5 sorry Si2O5 minus 2. Example clay. So in sheet silicate, what is the thing? So SiO4 unit, you can see this SiO4 unit. They will share three corners. Share three corner. Okay. अब इसमें थ्री कॉर्नर कहाँ कहाँ पे शेयर हो रहा है देखो. So if I say this one, if I say this, consider this one. So one, two, and three. So they will share three corners. If you consider this silica unit over here. So this oxygen atom is sharing one unit, one corner. This oxygen is sharing one corner, and this also is sharing one corner. So when one silica unit will share three corner, the structure formed is an infinite two-dimensional sheet of empirical formula Si2O5 minus 2. So sheet silicate, which is also called as pyrosilicates, will have how many corner sharing? Three corner sharing till now. Till now, was there any three corner sharing? There was no three corner sharing, right? In this, two corners were shared in chain silicates. Cyclic silicate also two corners were shared, but it was cyclic in nature. And before that, in pyrosilicates, one corner was shared. And orthosilicate, there was zero sharing, right? So ortho is sharing zero thing, pyro is sharing one corner, cyclic is sharing two corners, but it eventually leads to formation of a cyclic structure. Chain may also it is sharing two corners, but it's an open structure. Okay. And when two chains are joined to each other, in that case also we are seeing double chains form. But again, the sharing of atoms, how many corners are shared? There are only two corners which are shared. But if we go for sheet silicates, in this we are going to share three corners of the tetrahedron unit of the tetrahedral unit. Is that clear? So let's say if you consider the terminal ones like this, so in this you will only see these two corners getting shared. But if you see this bond, this oxygen is vacant, right? यहाँ पे we are not making that structure, but actually this is also getting this corner is also shared with something, but you can't draw this hole completely. So you can take it from here. You can consider this one a tetrahedral. You'll realize that okay, this oxygen atom is shared, this corner is shared, one corner here, one corner here, and one corner here. So total three corners are shared for sheet silicates. So total five silicates we have studied till now. Orthosilicate, zero corner shared. Pyrosilicate, one corner shared between two tetrahedron. Then comes after pyro comes what? Chain silicates, right? In chain silicates, sorry, cyclic silicates. In cyclic silicates, we have shared two oxygen atoms, or two corners are shared. In chain silicates, the open chain, two corners are shared. In closed chain also, two corners are shared. But in sheet silicates, we are sharing how many corners? Three corners are shared. Okay. A large number of sheet silicates are important and well known. These have slightly more complicated structure and are made up of either two or three layers joined together. These include clay minerals. Please remember the name kaolinite, pyrophyllite, talc, white asbestos, which is cryosylite and biotite, and micas. So these are all the sheet silicates which are there. Okay, these are the examples of sheet silicate. The clay minerals like kaolinite or pyrophyllite. इस पे याद रखना asbestos and mica are the example, prime example of sheet silicates. And white asbestos को they are classified as cryostyle and biotite. Mica is classified as muscovite and margarite. So these are like Mica's further classification. This is, and white asbestos is further classified, or it is found in this minerals. You can say. Okay. So, a large number of sheet silicates are important and well known. These have slightly more complicated structure and made up of either two or three layers joined together. So, sheet, what do we mean by sheet? So, overlapping of sheet will be there. So, that is what is two or three layers joined together. Is that clear? So, when we say that two or three layers are joined together, we are saying that two or three sheets are formed above each other. Okay. Now comes the three-dimensional silicate, 3D silicates. So, in 3D silicates, all four corners are shared. Can you see this? Sharing all four corners of a
Sir,
SiO4
could you
tetrahedron.
show the previous slide 1 second?
This one.
Yes. Yes.
Okay. Three-dimensional silicate. So, till now we have seen that the maximum shared corner was how much? Three corner. And that in the previous case. What was the previous case? Sheet silicate. Okay. Also called as phyllosilicates. So, in sheet silicate, we used to share three corners, but in three-dimensional silicate, total corner shared will be how much? Four corners of SiO4 units are shared. Okay. In a three-dimensional lattice formula of SiO2. So, uh, you won't be able to see it properly, but if you see, chalo, we'll consider this one. Yeah. See, this is one oxygen atom shared, second oxygen shared here, third is shared here, and this is the fourth one which is shared. Okay. Sorry. Am I clear to everyone? So, three-dimensional silicates are those silicates in which all four corners of a tetrahedron units are shared. Am I clear to everyone? Total, how many silicates we have studied till now? Six. First one was, yes, tell me. Ortho, yes or no? Second,
Yes, sir.
second
Pyro,
was pyro. Third was cyclic. Fourth was
chain,
chain. Fifth was
double chain.
नहीं और chain के अंदर ही हमने double chain वाला पढ़ा.
Oh,
Before this we studied
All the three
sheet
chains.
silicates. No,
sheet,
sheet silicate. And the last one is what? Like the in which we share four tetrahedron is
3D.
what? Three-dimensional silicates. Okay. And three-dimensional silicates. उसका देखो for sheet silicates, what are the example? Clay mineral. याद है? Then asbestos, white asbestos, and mica. These are all example of sheet silicates. Okay. So orthosilicates में zero sharing. Pyro में one corner was shared. Then cyclic में two corners were shared. Then chain may be two corners were shared, but what is the difference? Cyclic is a closed structure, chain was open. Is that clear? In double chain also, how many units were shared in double chain? Two corners were shared. Then comes after double chain, what was there? Just before this, what we studied? Sheet
Sheets.
silicates. In sheet silicates, how many corners of the tetrahedron units are shared? Three. And in three-dimensional silicates, we have shared four corners. Okay. Now, for a few more examples, like instead of silicon, if we have like some, like if we have some other metal as well in, like if we have to study some other metals other than silicon, can we see that? Yes, we can. So if you see zeolites, in zeolites, if you see if aluminum atom replaces few silicon atoms in three-dimensional network of silicon dioxide. So if you see this structure, this is of SiO2, no? 3D structure of SiO2. So if few of the silicon atoms are changed by aluminum, then it would be called as zeolite. It will be called as what? Zeolite. Okay. Overall structure will be known as aluminosilicate. Overall structure will be known as aluminosilicate. See, each silicon is sharing all the four, no? See, all four atoms are shared. Similarly, one of the silicon is replaced by aluminum. In this case, you can see that this aluminum which is there in before this we had silicon over there. Okay. So in such cases, those silicates will be called as aluminosilicate. Those silicates will be called as aluminosilicates if aluminum goes and replaces silicon atoms. Okay. Cations such as Na plus, K plus, or Ca plus to balances the negative charge. So these cations will be used to balance the negative charge. Examples are feldspar and zeolite. Okay. So what is the role of cation? To balance the negative charge. Because we all know total negative should be equal to total positive charge. Yes or no? Tell me. Have you understood what I'm trying to say? See, silicon was plus 4. No. What was silicon? Plus 4. But aluminum is plus 3. So still we require plus 1. No. So therefore this sodium metal is used. You got the point. Because SiO4, what is the overall charge? Minus 4. No. On one tetrahedral unit, what is the overall charge? Minus 4. SiO4 minus 4. Yes or no? So to balance minus 4 charge, we require plus 4 charge. So silicon was plus 4. But what about aluminum? It is boron family, so it is plus 3. Therefore, we require one more plus charge. So we take sodium plus. Is that clear to all? You can also take potassium plus. Zeolites are widely used as catalyst in petrochemical industries for cracking of hydrocarbon and isomerization. What is cracking of hydrocarbon? Do you remember cracking of hydrocarbons? Hydrocarbon chapter, you would have studied this reaction. Cracking of hydrocarbon results into what? Conversion of higher hydrocarbon into lower hydrocarbons. Yes or no? Tell me. You remember this cracking reaction in hydrocarbons chapter? Please tell me. Do you remember
Yes,
this
sir.
or not? Okay. So what is the catalyst for that reaction to be performed? Zeolites. What are the catalysts? Zeolites. Okay. Example ZSM5, a type of zeolite only. It is used to convert alcohols directly into gasoline. So what is gasoline? Do you know what is gasoline?
Petrol. Petrol.
Petrol only. Yeah. So petrol the company का नाम था. The name of company was petrol. The product is called as gasoline, but now we all call it petrol only. Is that clear? Petrol was the name of company that started to sell gasoline. But in India, petrol is famous. Like everywhere, petrol only is famous now. Is that clear? जैसे वो होता है ना, if you see that a brand becomes so goated that all its competitor, they are known by the same reason. Pani koi bhi, if you take any mineral water, if you go to that shop and you say, "Make Bisleri dena," it might give you any other bottle as well, but you will ask for Bisleri. Bisleri is the brand. Understood? Similarly, gasoline was the uh, product, but petrol was the brand. So nowadays it is called as petrol only. Anyway, leaving that. So, hydrated zeolites are used as ion exchangers in softening of hot water. So a few application of zeolites are what? First of all, it is used in petroleum industry for performing what? Cracking and isomerization reaction. And the special type of zeolite is ZSM5, which perform or which converts what? Alcohols into gasoline. So second application is this. And third application is what? It is used as a water softener. It is used as what? It is used as water softener. By which method? By ion exchange method. By which method, guys? By ion exchange method. So three application of zeolites we have done. First, catalyst in petrochemical industries. Then it is a special type of zeolite, which is what? ZSM5 converts alcohol to gasoline. And third one is what? It is used as a water softener by performing ion exchange. Identify the correct statement from the following. Carbon dioxide gas is used as refrigerant for ice cream and frozen food. Is it correct or incorrect? CO2 gas is used as refrigerant for ice cream and frozen food. Is it correct or incorrect? First statement, tell me.
Incorrect.
Correct.
Correct.
Correct
Isn't
or
it
incorrect?
solid? Isn't
Not
it
Wrong,
correct.
wrong,
solid?
wrong.
Yeah, CO2 solid is dry. No, CO2 gas is gas. Dekha? So be careful. So this is incorrect. The structure of C60 contains 12 6 carbon rings and 25 carbon rings. Correct or incorrect?
So incorrect. It's the other
Incorrect.
way around.
It's the other way around. Sure. Third statement, ZSM5, a type of zeolite, is used to convert alcohols into gasoline. Correct or incorrect?
Correct.
Correct.
Correct. Fourth, CO is colorless and odorless gas. Correct or incorrect?
Incorrect.
Correct.
What? Correct or incorrect? Correct, no. Colorless and odorless. No, CO is colorless as well as odorless. CO odor है क्या? Hmm? When we studied CO as odor, carbon monoxide is colorless and odorless, no? बोलो बच्चों,
हाँ सर.
what is the correct option then?
D.
D, D.
Who said B? Someone said B.
No, sir. D. Like
D, yeah.
A B C D.
D. Yeah. Okay. Yeah. Second वाले में it was the other way around. शाबाश. चलो, moving on. Which statement is wrong? Beryl is an example of cyclic silicate. Do you remember beryl? Hmm? Beryl क्या था? B3Al. B3Al.
Al2.
Mg2SiO4 is orthosilicate. Correct?
Yes.
Is it correct? Orthosilicate. Orthosilicate में क्या होता है? Total positive should be equal to total negative. So ये तो correct है. अच्छा, they are asking the wrong statement. Basic structure unit in silicate is the SiO4 tetrahedron. That is also correct. Feldspar are not aluminosilicates. क्या लगता है? Which is incorrect? Like which statement is wrong in this? Hmm? Zeolite and feldspar. Feldspar हमने कहाँ पे पढ़ा था? Zeolite वाले केस में पढ़ा था ना? Beryl is an example of cyclic silicate. Where you have studied beryl? B3Al. Do you remember that beryl wala part? Where did you study this?
Cyclic
Total
silicate.
plus 2. Cyclic silicate only. Sure.
Correct. Plus
Ah.
12 minus 12 1. Right.
Sure, no. So which option is incorrect according to you?
D.
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 हाँ.
Lock कर दिया जाए D. Good. So if aluminum atom replaces few silicon atoms in three-dimensional network of silicon dioxide, overall structure is known as aluminosilicates. They are known as what? Aluminosilicates. Okay. Examples are feldspar and zeolite. So feldspar वो ये हमने line पढ़ा था, तो why is this incorrect? Because zeolite I think it is aluminosilicate. Feldspar is not aluminosilicate. Okay. I think feldspar is not aluminosilicate. Zeolite is aluminosilicate.
So it's asking which statement is wrong. So feldspar are aluminum silicate.
Okay, ये इसने तो are not ना. Actually, these are example of aluminosilicate. Feldspar and zeolites are example of aluminosilicate. They are saying that feldspar are not aluminosilicates. ठीक है. By that, हाँ. Sorry, my bad. मैं इधर गड़बड़ा गया. Feldspars are not aluminosilicate, but they are. Zeolite and feldspar are aluminosilicates, right? So by that logic, it is wrong. Okay, correct. My bad. Which of the following anion is present in the chain structure of silicate? Chain structure of silicate. देखो ये सब बहुत इंपॉर्टेंट है. सिलिकेट्स के ऊपर यही सब क्वेश्चन आएगा कि हाउ मेनी कॉर्नर्स आर शेयर्ड. Okay, then what is the basic unit of that, like basic formula of that silicate? So you have to remember all of this. Like therefore, in each one you have to remember. जैसे SI orthosilicate में it was SiO4 4 minus, but after that was pyrosilicate. No, pyro में what one oxygen atom was shared, so it was Si2O7, and the overall charge was minus how much? कितना चार्ज था ओवरऑल? -7. No, Si2O7 -7, right? 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. 7. -7 था, -6 था। इसका बताओ, which of the following anion is present in the chain structure of silicate? Chain structure में which one is present? Chain में, you know ना, open chain, double chain is there. Open chain में there are two corners which are shared. So if two corners are shared, what will be the correct variant? Tell me.
B.
B. SiO3 -2. Sure.
A.
B or A? B or A?
Sir, B will be for the cyclic one, right?
B will be for the cyclic
This.
one. C is for SiO4 4 minus is what? Ortho one. The first one that we studied. Yes or no? And D is for the second one, pyro one. अब
The
बचता A
chain
और
also
B ही
the
है.
same. Chain also same formula was there, no? SiO3 2 minus.
हाँ, चेन और साइक्लिक का दिस वाज सेम ओनली SiO3 2 माइनस. ठीक है. सो ऑप्शन बी लॉक किया जाए. Yes or no? Someone said A as well, right? Someone
Yes.
said A, no? A is not for chain. See, oh, like at that time only we said no, कि chain and cyclic, their basic unit is same only, SiO3 2 minus. एक बार रिवाइज करना चाहिए तो. See, if you go through the units, okay, corners तो छोड़ दो. Yeah. For sheet silicate, what is the basic unit? Si2O5, overall charges -2. Okay. Then for chain silicate, you can use Si2O5 2 minus, or this is for double chain actually, not for chain. Chain के लिए we have this SiO3 2 minus. For cyclic also we had the same only, SiO3 2 minus. For pyrosilicate we had Si2O7 6 minus. Okay, because this oxygen atom is shared between both of them, no? So इसका तो double bond बना हुआ है. Actually it has two bonds, so it won't have any charge. When oxygen is present in single bond, in that case it will have charge. Here O minus 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 2, -3 total -6. So for pyrosilicate, this is the one, and for ortho, -4. SiO4 -4. Okay, this is formula for orthosilicate. For pyrosilicate, what is the formula? Si2O7 6 minus. Then comes cyclic and chain. Cyclic and chain have same unit. SiO3 -2. SiO3 -2. Okay. जो the oxygen which is shared, उसका negative charge will be gone. The oxygen which is shared, the negative charge for that oxygen will be gone. Okay. Yes or no? And for double chain silicate, you can have this kind of, like, this multiple things are there. Si2O5 -2, and the one that we have seen is Si4O11 6 minus. Si4O11 6 minus. This we have seen this. Okay. So अच्छा, इसमें the one getting shared, we don't have to count for them. Okay, the atoms which are getting shared, we don't have to count for their negative charge. So chain silicates के लिए you have multiple, please remember all of that. And then sheet में you have fixed Si2O5 -2. Okay, and then there is nothing mentioned for 3D silicate. 3D silicate में they have only said that the examples are feldspar and zeolites. चलो. हाँ. The basic structure unit of feldspar, zeolite, mica, and asbestos is. So feldspar, zeolite, mica, and asbestos, all of them are with silicates. Tell me. These are example of sheet silicates. These are example of which silicates? नहीं, सॉरी, माय बैड. फेल्डस्पार, जियोलाइट, ये तो हो गया. इसका है, क्या बोलते हैं, 3D का. मीका एंड एस्बेस्टोस कहाँ का है? मीका एंड एस्बेस्टोस आर sheet silicates, right? Mica and asbestos were classified as sheet silicate. But all of them, the basic structure unit is what? Tetrahedron only, no? SiO4 4 minus. Hmm? The basic structure unit for, see, if you go by classification, so feldspar and zeolite, they are 3D silicates, right? Yes or no? Feldspar and zeolite are what, guys? They are 3D silicate. But what about mica and asbestos? Mica and asbestos are sheet silicate. So you don't have to go for the basic unit. Sorry, you don't have to go for the shared unit. You have to go for the basic unit. What is the basic unit? At the end, all of them are silicates. No, what is the basic unit of silicate? Basic
SiO2.
structural unit of SiO2. Sure. SiO2 or SiO4 4 minus. SiO4 4 minus will be for orthosilicates or overall tetrahedron. Bro, what answer should we lock? SiO2 और SiO4 4 minus. देखो A and D तो नहीं होगा, ये तो सबको पता है. B and C में से what will be correct? Fast. Yes, tell me. Avnish, B or C? नहीं हो क्या
So,
अवनीश?
yes, I'm
निशांत? हाँ तो बताओ, आंसर बताओ. Tell me the answer. Which option will be correct? The basic structural unit of feldspar, zeolite. Acha, these are all a different classification. Okay, if you go by
B,
silicates
C,
classification, sorry,
C.
C. Okay. Others, yes, different. जो बाकी स्कूल वाले बच्चे हैं वो लोग भी बोलो. Tell me. The other student might also tell the answer fast. We don't have that much time. B or C? अवनीश
So
तुमने C
C.
बोला, right? C. Soham.
Yes, sir, I said
C.
C.
Yes, sir.
Okay. Others,
Yes, sir. See.
Yes, sir. C.
C. सबका C है. चलो. So some of the example of silicates जो इसमें mention कर रखा है कि because I told you know the thing is you don't have to classify them according to what? According to the silicate classification. Because if you go for that, then feldspar and zeolite belongs to sheet. Sorry, belongs to 3D, and mica and asbestos belong to sheet silicate. So you can't structurally classify them. So you have to consider their basic unit only. And what is the basic unit? SiO4 4 minus. Is that clear? SiO2 is this compound, silica compound. The first slide, if you open, you will see that SiO2 is the compound that we studied. Okay. SiO2 is what? Silicon. Silica is the compound. हाँ यार भाई, बहुत पीछे चला गया. See, SiO2 is the compound. SiO2 is silicon dioxide. Okay. So basic unit will be our of silicate will be SiO4 4 minus. Is that clear? This is the basic structure unit of silicates for all the silicates. Now, if you go for classification, so zeolite and feldspar, they are example of 3D silicate, whereas mica and asbestos are example of sheet silicates. So therefore, you can't use that this unit, right? The structural unit. So you have to go for their basic structural unit, which is what SiO4 4 minus. Name the type of structure of silicate in which oxygen atom of SiO4 4 minus is shared. In which one oxygen atom is shared?
C, sir.
Only one oxygen atom is shared in which case?
C.
Sorry? C. Everyone agrees. Only one oxygen atom, right? First one was ortho 0. Then comes pyro. Pyro may we share only one oxygen atom, right? 3D silicates may all four are shared. Sheet silicates may three are shared. Linear chain silicate. Linear chain may how much is shared? Two are shared, right? So pyrosilicate. I think we are on the end, yeah. So carbon forms two important oxides, CO and CO2, which we have already studied. This is just a revision kind of thing. Okay, well, we'll go through it quickly. This is a slide which can be used for revision of the PPT throughout the PPT, whatever we have studied. So carbon monoxide is a neutral gas, whereas CO2 is acidic in nature. Okay, and then carbon monoxide having lone pair of electrons, so therefore the attacking and that to carbon is the donor atom. So carbon forms metal carbonyls. The attack of electron density will take from carbon atom. Carbon monoxide is a deadly poisonous gas. Okay, and what does it do? It also goes and forms complex with hemoglobin and it replaces oxygen. Is that clear? So which results into what? Consciousness in the body. Carbon dioxide is as such it is not toxic like compared to like it is not toxic only carbon dioxide and CO is toxic. However, increased content of CO2 in atmosphere due to combustion of fossil fuel and decomposition of limestone is feared to cause increase in greenhouse effect. So the drawback of increased CO2 is what? The greenhouse effect that we see. Is that clear? Silica, silicates, and silicones are important class of compounds and find application in industry and technology. Silicates we studied total six type of silicates we have studied. Ortho, pyro, chain, then sorry, ortho, pyro, cyclic, chain, and chain mein then we have studied double chain also. Then comes sheet, then comes 3D. Total how much we have studied? Six. No, six type of silicates. And silicones, what are silicones? So silicones are alkyl derivative of silica. Silicones are what? They are alkyl derivative of silica. Silicon is what? Organosilicon, no? Silicones are called nothing but organosilicon based compounds. So it has carbon framework also. And we have seen silicones undergoes condensation polymerization. It undergoes what? Condensation polymerization. And for that, first it has to undergo the chlorosilane has to undergo hydrolysis, and then only we get what do we get? We get this hydroxysilane, which undergoes condensation polymerization to form long chain polymers. And if we have to control the length of carbon chain, which compound do we use to control the length of carbon chain? In
Uh,
condensation polymerization of silicones, which compound we use?
CH3 thrice SiC.
Very good. So it is called as trimethyl chlorosilane. What is it called as, Avnish? Trimethyl chlorosilane. And what does
Silane.
it do?
It
So
stops the
yeah,
chain.
it only has one OH, no? So
Yeah.
that the one OH that it has, it will participate in the condensation polymerization, and that will be the end of condensation polymerization. That's it. Okay. That's it for this part. So over, over. So can we leave the meeting, sir? Do you want to leave the meeting? See, we are done with this, but we have to start with S block. Okay, because still we have 1.5 hour time. So we are going to start with S block. Okay. Chalo, let me share the PPT. S block.
So can we have 5 minutes break and then we'll start?
कौन है ये जो रोज ब्रेक पूछता है? Yes, Mr. Sarang. Sarang, you only ask for break daily, right?
No, no. First time I'm asking.
Oh, first time you're asking. 5 minutes. Hmm. So you are muted. When I was muted. अच्छा 11:06. No man, I was not speaking Indian. ठीक है भाई. But ठीक है ले लो चलो. We will start 12:40 पे. 12:38 we will continue. S block, okay?
Yes.
I'm stopping the talk. Yes, guys, everything's back, right? Shall we continue? Hello?
Yes.
Okay. Sarang आया कि नहीं? Sarang, are you there?
Sir, I'm here. I'm here.
Okay. चलो. Hmm. So now the new chapter that we are going to start is S block elements. Okay. S block में how many groups are there? Everyone knows how many groups are there, right? How many groups are there? Two groups are there for S block. What are those two groups? Group one and group two, right? Yes or no? Group one elements are called as alkali metals and group two are called as alkaline earth metals. That also we are aware. Okay, directly will proceed with the PPT. So, just a minute. Okay, this is periodic table. Laser, no, laser. Yes. Now, so you can see we have to study group one and group two. So this Lina ka rubber chore France लेके this family and beta मांगे transporter बाप राजे. These two family we have to study. Okay. So group one में these are the element lithium, sodium that we already know, and they form strongly alkaline hydroxide with water. So when they will react with water, what do they form? They form base. They form alkaline hydroxide. Is that clear? Collectively known as alkali metals. Group 1 are known as alkali metal, group 2 are known as alkaline earth metals. So the alkaline earth metal, their oxides and hydroxides are alkaline in nature, and these metal oxides are found in Earth's crust. They are found in what? Earth's crust. Is that clear? Therefore, you would have studied that they are called as alkaline earth metal because these metal oxides they exist in the Earth's crust. Okay? Now, these are the elements which are present in group 2. Anyway, we all know all of this. And then general electronic configuration of sorry group 1 is what? Noble gas and NS1. Noble gas means what? Nearest noble gas configuration. For lithium, the nearest noble gas is helium. So the electronic configuration will be helium and then it comes 2s1. Right? Sorry, helium 3s1. So क्या बोल रहा हूँ मैं 1s2 then अपना lithium का हो जाएगा it is 2s1 1s2 2s1 so instead of writing 1s2 2s1 you can write it as helium 2s1 so that is noble gas but for sodium you're going to get neon 3s1 like that understood now this is the electronic configuration then atomic and ionic radii what we all know down the group if we move what happens if we move down the group size increases no if size increases then atomic and ionic radii will increase so down the group atomic and ionic radius increases. Now, because they are metals, so metals are electropositive element. What is meant by electropositive element? What happens? So they will lose electron. So they readily lose electron to give unipositive ion, which is what? M plus ion. Is that clear? And never found in free state in nature. So this electropositive, this group one elements are never found in, they are never found in free state in the nature. Is that clear? Now what about ionization enthalpy? We all know as the size increases, ionization enthalpy decreases. So down the group, when the size will increase, ionization enthalpy will decrease. And therefore, highest ionization enthalpy is for lithium, followed by sodium, potassium, rubidium, and cesium. Now, hydration enthalpy. What about hydration enthalpy? You know, hydration enthalpy is directly proportional to charge and inversely proportional to size. Therefore, we write smaller the ion, that is, if size is small, then hydration energy will be more. Why? Because hydration energy is directly proportional to charge and inversely proportional to size. And that charge to size ratio is called as charge density. Charge to size ratio is called as charge density. So higher the charge density, higher is the hydration enthalpy. And charge density is nothing but charge upon size. So if charge is more, hydration enthalpy is more. If size is less, hydration enthalpy will be more. Because लिख दूं क्या यहाँ पे? I'll write it over here. That hydration enthalpy directly proportional to charge and inversely proportional to size. Is that clear? So this charge to size ratio is called as charge density. Am I clear to everyone? Therefore, we all know that lithium plus has the highest hydration enthalpy. Why? because charging same on all of them, but lower the size, higher the hydration enthalpy. So lower size is for lithium ion. Therefore, it has the highest hydration enthalpy. Understood? Moving on. Melting point and boiling
Before the
point. Oh,
previous slide. No, the one before this.
the one before this.
Yes. Okay.
See, because you have already studied all of this, therefore I am being a little quick. So we can give more time to the topic that you have not studied. You have
Yes,
studied,
sir.
all of you have studied this one option, therefore I was little bit quick. But if you are facing problem, please let me know. So ionization enthalpy over.
Yes. Sir.
Can you proceed? Hydration enthalpy understood. See, hydration enthalpy is directly proportional to charge and inversely proportional to size. But if you see, charge is same, plus one, plus one, plus one, plus one, and plus one. So it means if charge is same, then who is the deciding factor? Size. So hydration enthalpy is inversely proportional to size. Therefore, lower the size, higher the hydration enthalpy. Which size is the lowest? Lithium. Therefore, it has the highest hydration enthalpy. Therefore, it has the highest hydration enthalpy. Can you proceed? Sorted. Down the group, hydration enthalpy decreases. Why? Because size increases. Can you proceed?
Yes, sir.
Oh, melting point and boiling point. So, group 1 elements have low melting point and boiling point due to weak metallic bonding. See, only single valence electron are present. No. You have studied metallic bonding concept in chemical bonding. Tell me. So, in that, you would have studied that what is metallic bonding. So, this electron which are negatively charged and the ion which are positively charged, they will have interaction with each other. Is that clear? Because single valence electron is there, so that interaction, electrostatic interaction will be very less. The electrostatic interaction will be very less, and as a result, the metallic bonding is very weak. Because of weak metallic bonding, all the elements are very soft in nature. You can see this group 1 elements, these group 1 metals are soft metals. And therefore, they have low melting point and boiling point. What is the reason? Because of weak metallic bonding. Okay. So, what are the properties that we have studied? What are the properties that we have studied? Tell me. Melting point before that, melting point and boiling point before that, what we studied? Ionization enthalpy, hydration enthalpy, and see, electronic configuration and atomic and ionic radius. These 5 properties we have studied, right? Now, if you have to answer this, as compared to potassium, sodium has, which option will be correct? Sodium has what?
B.
B. Higher ionization potential. Very good. Because down the group, ionization enthalpy decreases. So therefore, potassium will have lower ionization enthalpy compared to sodium. So sodium will have higher ionization. Okay. Which of the following statement is correct regarding alkali metals? Yes. Fast. We all know na size of cation is smaller than the atom. Size of anion is bigger than the atom. Which of the following statement is correct regarding alkali metals? First is saying that cation is less stable than the atom. Second, cation is smaller than the atom. Third, size of cation and atom is the same. Is it true? No. Atom is bigger in size than cation. Cation is greater in size than the atom. Atom. That is also wrong. Which option will be correct? Tell me. For alkali metals or for any ion, like any atom is bigger than its cation, is larger than its cation. Is that clear? Tell me. Any atom is larger, is always larger than its cation. It's smaller than its anion and larger than its cation. So which option will be correct? Fast.
Sir, option
That
D.
I'm option B. Someone said B, I guess. How B, beta? I just
Sir,
said
I
that
said B. B.
B.
Cation is
Sorry, my bad.
smaller.
My bad. Okay. Some okay. Option B correct. ठीक है. Moving. Flame test. Alkali metals, acha, they have valence electron, no? One electron in the valence shell. So what happens when you heat them? Flame test mein what do? We heat the metals. So alkali metals and their salt impart characteristic color to oxidizing flame. Now what happens when we heat them? So the valence electron which is there, it gets excited. Okay, excited means what? Its energy will increase. And on de-excitation, what happens? It releases color. It releases energy, no? Excitation, de-excitation, you are studying the structure of atom, right? So for excitation, it requires energy, but on excitation, it becomes unstable. So it wants to become stable again. So it will undergo de-excitation. While de-excitation energy is released in the form of heat or light. So in this case, in the flame test, they release the energy in the form of light. Therefore, you will see this color. So you have to remember these colors, okay? You have to remember this color. So on heating lithium or its salt, we get crimson red color. On heating sodium, we get yellow color. On heating potassium, we get violet or lilac color. On heating rubidium, we get red violet color. And on heating cesium, we get blue color. And what is the reason of this color? The reason is, yes, what is the reason of this color? Excitation and de-excitation process. Okay. So when energy is supplied, electrons get excited, but on de-excitation, they have to release that excess energy. That energy is released in the form of color or in the form of light. So this light rises in the visible range, therefore we get to see all these colors. Okay. Now, chemical properties of group one element. So they are highly reactive. All these group one elements are what? Highly reactive. Why? Due to their low ionization enthalpy. Okay, the reactivity of this metal increases down the group. The reactivity of these metals increases down the group. Why? Because down the group, ionization enthalpy decreases further. Yes or no? It becomes more lower. Therefore, its reactivity will increase. Because of their high reactivity towards air and water, they are normally kept in kerosene oil. And you would have studied. So, if you have you performed that sodium fusion test in laboratories, lab when it will be started, you will be doing that sodium fusion test. Okay. So when you take sodium fusion test with sodium, you would see that sodium is kept in kerosene. You would have seen some videos on YouTube as well, no, or Instagram reels. That when sodium comes in contact with water or moisture, it explodes. It results in explosion, right? Hydrogen gas is released. So therefore, all alkali metals are very high reactive towards air and water, and therefore they are kept in kerosene oil. They are kept in what? Kerosene oil. Okay. Now, this is very important. So, reaction with air. Reaction with air. So, when alkali metals undergo reaction with air, so the smaller metal like lithium, it will form oxide, lithium oxide. But sodium forms peroxide. Sodium forms peroxide. And other larger metals, because potassium, rubidium, cesium, these are larger in size, no? So they form superoxide. What do they form? Superoxide. Now, what is the logic, sir? Why is it like that? Okay, first read this point. Alkali metals tarnish in dry air due to the formation of their oxide. Okay, we all understood this. But all alkali metals will they form oxide? No, only lithium form oxide. Why? Because oxide is a small ion compared to peroxide and superoxide. Okay, oxide is a small ion compared to peroxide and superoxide. Therefore, what happens? For larger size, we require larger ion. Therefore, larger cation will require larger anion. Superoxide will be larger in size compared to peroxide and oxide. Peroxide is larger in size compared to oxide. So, sodium will form peroxide and others will form superoxide. Okay, but lithium will form lithium oxide, Li2O. So, please remember this the reactivity with air or reactivity with oxygen basically. Okay. Only lithium form oxide, the sodium forms peroxide, but other metals like potassium, rubidium, cesium, they will form superoxides. Okay. Now, size of the metal ion when it increases, stability of peroxide or superoxide increases. We all studied this. Like just now, I told you the reason, right? Why peroxide is or superoxide is formed. So, as the size will increase, of cation, it wants a larger anion to interact because the compatibility of size should not be the issue, right? And if size is almost same, then the overlapping and the bond formation will be good. Therefore, they prefer, like larger cations prefer larger anions. Is that clear? Due to the stabilization of larger anions by larger cations through lattice energy effects, we say that like this formation of oxide and peroxide and superoxide will vary. Is that clear? Tell me. You understood? No? The main reason is what? So larger cation requires larger anion and smaller cations require smaller anion, as simple as that. So potassium, rubidium, cesium, they are larger elements, they are larger cation. They will require larger anion like superoxide or peroxide. Got my point? Can we proceed? Now, reaction. So be it oxide, superoxide or peroxide, all of them will undergo hydrolysis. All of them will undergo hydrolysis. And what do they form? They form hydroxides. They will form metal hydroxide. So it does not matter whether it is oxide, peroxide or superoxide. The main product will always be on the main product on hydrolysis of such oxides will always be hydroxide. Will always be what? It will always be hydroxide. Am I clear to everyone? Tell me. So what you have to remember, see, for group one elements, the till now the exceptional part that you have studied is the forming, is the reaction with oxygen. So lithium on reaction with oxygen will form lithium oxide. Sodium will form peroxide, but potassium and onward will form superoxide. What they will form? They will form superoxide. Understood, guys? Tell me. And it does not matter whether they are oxide, peroxide, or superoxide. All of them on hydrolysis will give us hydroxide, metal hydroxides. Understood? Now, lithium shows exceptional behavior in reacting directly with nitrogen at room temperature. Okay. Other members of this group do not react with nitrogen directly, but lithium reacts with nitrogen and forms lithium nitride. What does it form? It forms lithium nitride. Is that clear to everyone? So this reaction is there. So reaction of nitrogen will only take place with lithium. It won't take place with other elements of the group. Am I clear to everyone? See, lithium shows very exceptional behavior in this group. And we have a dedicated topic for exceptional behavior of lithium. So there is this is also present in that topic. Okay. So lithium, compared to other member of that group, will deviate from some of the reactions and properties, and which are studied under the topic we called exceptional behavior of lithium. Okay, reaction with metal or with water. So when metals will react with water, what will happen? They will form hydroxide. They will form metal hydroxide, and hydrogen gas will be released. They will form hydroxide and metal gas. They will form metal hydroxide and hydrogen gas will be released. So this is for all alkali metal. Alkali metals on reaction with water will form alkali metal hydroxide and hydrogen gas is released. Okay. Now, have you studied E naught value? In redox chapter, we would have discussed something of E naught value, right? So we say that higher the E naught value, okay, higher the negative E naught value, higher is the reducing power, okay, and higher is the reactivity also. Higher is the reducing power and higher is the reactivity also. So if you go by that logic, lithium has the most negative E naught value, and most negative E naught value means the most reducing agent among all the group one member and the most reactive one as well. Okay, but its reaction with water is less vigorous than that of sodium, which has the least negative E naught value among the alkali metal. The reaction of K is even more vigorous than sodium. Now, sir, just now you told that higher the negative E naught value, higher is the reducing power and higher is the reactivity. Yes, it is. But for lithium, I told you, the size is very small. The size is very small. So when it comes in contact with water, it undergoes hydration very easily. Is that clear? Lithium undergoes hydration, and therefore it can't react vigorously with water. It undergoes what? It undergoes hydration. It undergoes what, guys? It undergoes hydration. So it can't react with water that comfortably compared to other species. Am I clear to everyone? So it won't undergo hydrolysis. It will undergo hydration. Lithium shows hydration. Therefore, this exception is there. Even though it has the highest E naught value, but the reactions with water is less rigorous for lithium compared to sodium. Am I clear to everyone? In electrochemistry, also you'll study this E naught value. Don't worry if you have forgotten for redox chapter. But as of now, what you know, what you should know is if higher the negative E naught value, like, and higher will be the reducing power and higher will be the reactivity. Okay. Since the melting point decreases down the group, the reaction with water becomes more and more vigorous. Okay, more and more vigorous. Acha. And you have a kinetic factor, thermodynamic factor. You won't, like, it won't be easy for you, but still I'll try to explain. देखो होता क्या है? There are two reasons for this. एक तो hydration हो जाएगा, so it becomes thermodynamically more stable, right? So therefore, we say that even though lithium has highest negative E naught value, okay, so it should be the most reactive one. But because of hydration, it becomes stable. So it does not react only. Is that clear? Are you getting my point? And therefore, because it does not react, its reaction is less vigorous compared to the reaction of sodium with water. First point. And when hydration occurs, it becomes thermodynamically more stable. It becomes thermodynamically more stable. So rate of reaction of lithium and water will be less compared to the rate of reaction of sodium and water. Am I clear to everyone? Because sodium has higher size compared to lithium. So its hydration energy will be hydration energy for sodium will be less compared to lithium. Lithium in the hydration energy is the highest. Okay, in that group. So, so there are two reasons. First, we all know that highest E naught value means most reactive one, but still it is less rigorous. It is reacting less rigorously with water. The reason is what? Thermodynamic angle. Because lithium ion is thermodynamically more stable in water. Okay, but because it is thermodynamically more stable, but the rate is less. Rate is higher for sodium water reaction. The rate is higher for sodium water reaction. This is what is discussed over here. Okay. So reaction is kinetically faster. Which reaction? The other reaction of water with the other metals, other alkyl metals. I cleared everyone. Do you have any doubt till now? You want to ask something or we can continue?
Sir, why is the melting point dependent here?
Sorry.
So like here this said that the melting point decreases, the reaction becomes more vigorous.
The reaction with water becomes more and more vigorous. See, melting point decreases. इसका मतलब like, how is it related? So down the group, softness of metal is uh, increasing. No, if melting point is decreasing, the softness of metal is increasing. Then the compatibility or the mixability of the metal in water will be more. Understood?
Okay, so yes.
Yeah. And one more thing is the surface area exposed to water. See, when the softness will increase, then you can say उसमें the metal won't be rigid in that case. Is that clear? If it is not rigid, you can imagine it as expansive metal or it is undergoing expansion like that. Okay, so surface area will be more comparatively. And when some surface area will be more, what will happen? The reaction or the interaction of metal with water will be more. Therefore, a reaction will be kinetically faster. It means rate of reaction will be more because the number of interactions are more. See this concept and or whatever. First, you understood that point. That how what do I mean by like what does this melting point decrease associate with the reaction of water with alkali metals? Why it becomes vigorous? Because down the group softness will increase, and so considering the metal is not rigid, surface area will be more as we move down the group. So reaction will be kinetically faster because more interaction will take place at that time. What will take place? More interaction will take place at that time. Okay, बढ़िया आगे. ये वाला पॉइंट याद रखना प्लीज लिथियम का एक्सेप्शनल बिहेवियर में आएगा ओके एट द एंड I'll brief or I'll list all the exceptional behavior of lithium as well but as of now please remember this point कि even though E naught value is highest for lithium but it becomes thermodynamically more stable due to hydration therefore what will happen the reaction is less vigorous for lithium compared to other antimons, other metals. This thing you have to remember. And then down the group, melting point will decrease, surface area will increase. So reaction of water with alkali metals, the interaction will be more, and hence the reaction will be more vigorous because surface area of the metal will increase. So when the surface area of metal will increase, the interaction of water molecule on the surface of the metal will increase. As a result, more reaction will take place, or the reaction will become faster. Okay. Now reaction with dihydrogen. So when alkali metals will react with dihydrogen, what do they form? They form metal hydrides. They form, what do they form? They will form metal hydrides. Is that clear? Alkali metals react with hydrogen to form ionic hydrides. What do I mean by ionic hydride? It means they are ionic in nature. They are not covalent. Okay. M plus and H minus. You can see this representation. M plus and H minus. Stability of hydride decreases down the group. Why, sir? Why does it decreases down the group? Because down the group, metal size will increase, but size of hydroid is fixed. No, hydroid is fixed, but down the group, size of metal will increase. Because size of metal will increase, what will happen? That the bonding or the bond strength of the metal and hydrogen will decrease. The bond strength of metal and hydrogen will decrease. Understood? Therefore, stability of hydrides down the group decreases. If bond strength is less, it will break easily. No, so stability will be less. Got my point? What do I mean by this, everyone? So when metal, alkali metal react with dihydrogen, it forms metal hydride. They are ionic in nature, and down the group, the stability of hydride will decrease. Reaction with halogens. So what happens when metal react with halogen? It will form metal halides. Okay, it will form what? Alkali metal halides. And again, they are also ionic in nature. They are also what? They are also ionic in nature. Okay, moving on. So reaction with dihydrogen and reaction with halogen for the alkali metals is done. Both of them form ionic compound as the final product. Okay, and for metal hydride, you have to remember of the stability. The stability of metal hydride bond will decrease down the group. As a result, stability of hydrides decreases down the group. Lithium halide have more covalent character because of higher polarization capability of Li plus. Fazan's rule you have studied, everyone, right? What does it say? It says that for cation, polarizing power is directly proportional to charge, inversely proportional to size. But for anion, polarizability is directly proportional to charge and directly proportional to size. It means if cation is smaller in size, covalent character will be more. And if anion is bigger in size, covalent character will be more. Is that clear? Because for anion, size is directly proportional, and for cation, the size is inversely proportional. Is that clear? Therefore, lithium halide mein halide will be, let's say the halide is common. Okay. So we have written that lithium halide have more covalent character because of the high polarization capability of Li plus ion. Because if size is small, then what will happen then? Polarization of the cation will be more.
The
Because we know
polarization is directly proportional for
polarizing power.
cations.
For cation we write polarizing power. You want me to write this? We say that polarizing power of cation directly proportional to and inversely proportional to size. But polarizability directly proportional to charge and directly proportional to size. So for anions, we define polarizability, and for cation, we define polarizing power. Cation goes and polarizes the anion. Anion is polarized. So polarizability for anion and polarizing power of cation. Okay. So lithium has the smallest size among all the alkali metals. No. Therefore, it will have the highest polarizing power of cation. Is that clear? Understood. Now read this part. Since anions with large size, laser. Yeah. Since anions with large size can easily be distorted, lithium distorted means what? Polarized. For anions, it can if the size is large, then we know now polarizability of anion is directly proportional to size. It means if size is more, then polarizability is more. Is that clear? This is what we have written, that since anions with large size can be easily be distorted, lithium iodide is the most covalent in nature. Lithium iodide is the most covalent in nature because iodide ion, if you compare all the halide ion, F minus, Cl minus, Br minus, I minus, they are all anion. No. So in that case, covalent character will be directly proportional to size. Covalent character will be because higher the polarizing power or higher the polarizability, higher is the covalent character. And polarizability of ion is directly proportional to size. Is that clear? So therefore, I minus will have the highest polarizability in among all the anion of halogen family. Therefore, because it has the highest polarizability, it has the highest covalent character, and that is what is written over here. That since anions with large size can easily be distorted, lithium iodide is the most covalent in nature. Am I clear to everyone? Now, halides having ionic nature have high melting point and are good conductors of electricity in fused state. Do you believe it is true? Obviously, because first of all, they are ionic in nature. Okay. And what will happen? So if you heat them, fused state means what? If you heat them, so it will form ions. So positively charged metal and negative charged halide ion. So now these ions will conduct electricity. Therefore, we say that high ionic nature halide have which have high melting point, they will be good conductor of electricity in fused state. Why? Because uh, if you heat them, they will be converted to respective ions, and when ions are formed, they can conduct electricity. Is that clear? And these alkyl halides, alkali metal halides are readily soluble in water. Why? Why alkali metal halides are readily soluble in water? Can anyone tell me?
They are ionic, so they will get split when dissolved.
Sorry. Continue.
So they're like polarized. They can be polarized into positive and negative, right? So polar solvent and polar molecule. So they'll get
देखो सिंपल सी बात है solubility depends on which factor. Light dissolves light. Solubility depends on which factor, guys? Light dissolves light. इस बात को मत भूलो. Don't forget this. Okay. So now when we say that alkali metal halides are readily soluble in water, it is because they are polar in nature, positively and negatively charged. So water is also polar in nature. Understood? So therefore, polar will be dissolved in polar very efficiently. Therefore, they are readily soluble in water. Moving on. Acha, solubility. In chemical bonding, you would have studied solubility. Solubility is dependent on two other factors. Can you name those two other factors on which solubility is dependent? Anyone? Lattice enthalpy and
Temperature
hydration
and
enthalpy. No. It is dependent. Like the two other factors which I'm saying is so the temperature and all is there. Okay, but
uh,
like the competing. I was talking with reference to chemical bonding. No, so in chemical
oh,
bonding, you would have studied that solubility is a competing power between lattice enthalpy and hydration enthalpy. Is that clear? Solubility is nothing but it is the competing nature between lattice energy and hydration energy. Have you studied this in chemical bonding? First, tell me this. You remember whatever you have studied in chemical bonding? Hmm? Tell me, everyone. So, when do we say that ionic compound will be soluble in water? So, if hydration enthalpy is greater than lattice energy, then we say solubility is there. But if lattice enthalpy is greater than hydration enthalpy, then solubility is not there, or it is insoluble. Like that, you have to see. Okay, can we proceed? Now, there comes the solubility. Okay, so here I'll write. See, for solubility, what you have to remove. That only I will write. Okay. Now, just now I told you that solubility is dependent on lot of factors. Okay, dielectric constant is there, But the factor that is more important to us in S block is lattice energy and hydration energy. Okay. So solubility solubility is dependent on lattice energy and hydration energy. Lattice energy and hydration energy. Okay. Now we say that for solubility of any compound in water, okay, the obviously that and thermodynamic condition should be satisfied. You know that delta G should not be negative. Is that clear? But what is the favorable condition? So we say that if enthalpy of hydration is greater than enthalpy of lattice energy, if enthalpy of hydration is greater than enthalpy of lattice energy, then what do we say? We say that it is soluble. Then the compound, ionic compound, then ionic compound is soluble in water. Then ionic compound is soluble in water. This is chemical, right? In water. Okay. So how do you check solubility? In that case, hydration enthalpy should overpower the lattice energy. Hydration enthalpy should overpower the lattice energy. Is that clear? So what do we say? देखो होता क्या है कि इन एस ब्लॉक यहाँ पे एंडाइटेड ओवर हियर इन एस ब्लॉक down the group in S block down the I think my screen is lagging. Sorry, my the pen tab and screen they are not in sync properly. Down the GROU down the group. So in S block down the group solubility of see it is lagging a lot. Solubility of most of the salt solubility of most of the salts decreases because why is it not ready on you man? Solubility of most of the salts decreases. That decreases is not written, it decreases. Decreases cause hydration energy decreases more rapidly as compared to energy. Because hydration energy decreases more अरे बाप रे बाप तो भयंकर लैग हो रहा है decreases more more rapidly so what I have written over here that in S block down the group solubility of most of the salt decreases because hydration energy decreases more rapidly compared compared to lattice energy. Compared to what, guys? Compared to lattice energy. Okay, compared to lattice energy. Okay, moving on. Now, what you have understood from this point, just analyze. So if you check over here, that lithium fluoride and cesium iodide. So high lattice enthalpy for lithium fluoride. Why? Why? Why is it high lattice enthalpy? And for cesium iodide, why it is smaller hydration enthalpy? Mhm. Why these both are low soluble in water? See, smaller hydration enthalpy depends on what? Charge and size, no? So cesium plus I minus. So charge is same, but size is highest for all of both them. Na? Cesium is highest in its group. Iodine is highest in its group in size. So if size is more, hydration enthalpy will be less. Size is more, then hydration enthalpy will be less. Understood? But what about lithium fluoride? You understood this? Wait, laser gone yet. What I mean to say from this point, cesium iodide, if you dissociate this, so it will become cesium plus and I minus. Cesium plus and I minus. Now cesium plus and I minus are there. Okay, fine. Now, what about hydration enthalpy? Just now, before some time, we have studied that hydration enthalpy is directly proportional to charge, inversely proportional to size. But charge is same for both of them, plus one and minus one. No. So charge is same. The magnitude of charge is one only. So charge is not the deciding factor. Then what is the deciding factor? Size. So size, if it is more, hydration energy will be less. Therefore, we say that smaller hydration enthalpy for cesium iodide. We say smaller hydration enthalpy for cesium iodide because size is very big for both cesium and iodide. Size is very big for both cesium and iodide. But what about lattice enthalpy? What is lattice enthalpy? What is this lattice enthalpy? We are not able to understand. Why high? Why we have written that it has high lattice enthalpy? Can anyone explain it to me? Why lithium fluoride has high lattice enthalpy? Because you have studied, no, lattice energy. See, like hydration is dependent on directly proportional to charge and inversely proportional to size. Lattice, may we say that it is directly proportional to charge. Lattice also and inversely proportional to size. Okay, lattice also directly proportional to charge and inversely proportional to size. Now, lithium fluoride. So if size is less, then lattice energy will be more. Yes or no? अरे जगह भी नहीं बचा. I use some different color. ठीक है. Green pencil, okay? Yes. So for lattice energy, what do we say? We say that lattice energy is directly proportional to charge and and inversely proportional to size. So charge is again same, plus one and minus one on lithium and fluorine, but size is less. If size is less, if size is less, then what will happen? Lattice energy will be more. Therefore, we have said that high lattice enthalpy. And low solubility. What is the reason of solubility? So solubility ke liye I have told you, hydration enthalpy should be greater than lattice energy. Hydration enthalpy should be greater than lattice energy. So basically, if you see for this compound, very high lattice enthalpy, so it won't be soluble in water. Okay, and similarly, this is very high hydration enthalpy. Again, sorry, very small hydration enthalpy. It means very small amount of energy is released. Therefore, this will also be not that much soluble in water. Is that clear? So solubility depends on two factors: lattice energy and hydration energy. If hydration energy exceeds lattice energy, then it will be more soluble. Then it will be more soluble. Okay. But if you see in these cases, lithium fluoride and cesium iodide, lithium fluoride is that compound which has the highest lattice enthalpy, and cesium iodide is that compound which has the lowest hydration enthalpy. Okay, so these two compounds are extreme and therefore they are very low soluble or almost insoluble in water. Am I clear to everyone? And for S block, as we move down the group, you can see it over here. Let me use the laser. What point I have written over here? Just read it along with me. that in S block down the group, solubility of most of the salt will decrease because hydration energy decreases more rapidly compared to lattice energy. Is that clear? Down the group, what happens? Hydration energy decreases more rapidly compared to lattice energy. Moving on. Now, reducing nature. See, reducing nature means what? To reduce something. And metals are good reducing agent. But because they can donate electron, what they can do? They can donate electron. Is that clear? So, reducing nature, if we have to see for alkali metals, then we say that the alkali metals are strong reducing agent. Is that clear? And you have studied this Born-Haber cycle. Have you studied Born-Haber cycle? Tell me. Has
Yes.
everyone studied Born-Haber cycle? Yeah. So in Born-Haber cycle, you would have studied that definition of ionization enthalpy. Also, you have studied that for an atom to donate electron. Now, what is ionization enthalpy? The energy, minimum amount of energy required to remove an electron from the from the outermost shell of an isolated gaseous atom. So first, solid metal will be converted to gaseous metal by sublimation. Now, this gaseous metal, which is here, will lose one electron. Is that clear? So, this gaseous metal will lose one electron. Okay. Now, after that, what will happen? So, this metal which is there, M plus, sorry, metal ion which is there, it will now undergo hydrolysis. It will now undergo hydrolysis and it will form aqueous metal ion. It will form what? It will form aqueous metal ion. Now, what do we say? We say that reducing nature depends on reduction potential. See that E naught value which we studied at that time. No, higher the negative E naught value, higher is the reducing power. Is that clear? This is what we mean by reduction potential. This reduction potential is nothing but E naught only that we discussed in previous slides. Okay. So reducing nature depends on reduction potential, which is resultant of all these factors: sublimation enthalpy, ionization enthalpy, and hydration enthalpy. It is a resultant of sublimation enthalpy, ionization enthalpy, and hydration enthalpy. Am I clear to everyone? What is resultant of this? The reducing potential, the reduction potential, the E naught value. So, E naught value comes from all these three factors combined. E naught value comes from all these three factors combined. Okay. Now coming to this point, lithium is the most powerful and sodium is the least powerful. Lithium is the most powerful and sodium is the least powerful reducing agent. This reducing tendency that we are talking in aqueous medium. In which medium we are talking, guys? The reducing power tendency here that we are talking, that lithium is the most powerful in its family and sodium is least powerful. We are talking it in which medium? We are talking it in aqueous medium. You can see this. We are all the studies related to aqueous medium. Is that clear? Therefore, uh, if you compare in gaseous medium, what will happen? Just electron donation. In gaseous medium, what is the case? The element which will donate electron easily is the best reducing agent. And who will donate electron easily in the whole lithium family? Tell me, who can
Cesium.
donate electron? Down the group, donation tendency will increase. Why? Because the outermost electron is very away from the nucleus. It is not receiving enough nuclear charge. As a result, it is more vulnerable for getting donated. Therefore, in gaseous state, the order will be the increasing order will be lithium, sodium, potassium, rubidium, cesium. Is that clear? Tell me. But that is not the case in aqueous medium. For aqueous medium, you have to consider sublimation enthalpy, ionization enthalpy, and hydration enthalpy. There, you have to consider all these three values. And based on all these three values, we prepare reduction potential chart. What do we prepare? We prepare reduction potential chart. Is that clear, guys? Therefore, see, due to the small size of lithium ion, it has the highest hydration enthalpy. Is that clear? Due to the
Yes.
small size of lithium ion, it has the highest hydration enthalpy that we have studied. So, if you see in gaseous phase, it is the same order that we have discussed. It is the same order that we have discussed. But in aqueous phase, you have to remember the order. In aqueous phase, you have to remember the order. Why? Why? Because in aqueous phase, the reducing nature is a combined study of ionization potential, then hydration enthalpy, yes or no? See, and sublimation enthalpy. So the E naught value that we have found out for all the element, it is a combined study of these three particular studies. Okay. But for gaseous, you have to directly remember that whoever will be donating the electron easily, they will have the highest releasing power. Okay. Now, what is written over here? Due to the small size of lithium ion, it has the highest hydration enthalpy. We know because hydration enthalpy is inversely proportional to size. So smaller the size, higher the hydration enthalpy. That we already know. Accounts for its high inert value and therefore has high reducing power. So lithium, because it has very high hydration enthalpy, so it has the highest reducing power. It has the highest reducing power in aqueous phase. Is that clear? Followed by cesium, rubidium, potassium, and sodium. So sodium is the least reducing in aqueous medium. Please remember this order, okay? Lithium, cesium, rubidium, and then potassium, green, rubber. What you have to remember is lithium is the highest, then go from bottom to top. So cesium, rubidium, potassium, and sodium, like that. See, in this case, it is the ascending order, right? छोटे से बड़ा. So lithium is the least, lithium is the highest. Here, lithium is highest, followed by uh, just invert the table from cesium. So cesium, then rubidium, then potassium, and then sodium. Please remember this order. This is experimental order, okay? And how we have got this order? By combined study of sublimation enthalpy, ionization enthalpy, and hydration enthalpy. What is the correct answer for this? What is the correct answer for this? Alkali metals may be arranged in the decreasing order of their reducing power in aqueous solution as. In aqueous solution, just now we studied, no?
C.
Correct option will be, I told you, lithium will be highest. Then after that, just start from bottom to top. So, cesium, rubidium, potassium, and sodium. That's it. Is that clear? So, which option is correct, guys? Option C. Now, chemical properties. See, this is a very important chemical property of group 1 metals. Okay. So, alkali metals, just a minute, let me use the laser. Alkali metals, yeah. Alkali metals, when dissolved in liquid ammonia, give deep blue solution. What do they give? They give deep blue solution, which is conducting, reducing, and paramagnetic in nature. Why is it like that? See, conducting is what? It will conduct electricity. And to conduct electricity, either you should have ions or electron, right? Yes or no? So, ammoniated electron or ammoniated metal, alkali metal when dissolved in liquid ammonia. Can you see this reaction? Metal with liquid ammonia. What do we get? We get ammoniated metal and ammoniated electron. So, this ammoniated electron which is present, it is unpaired electron, right? And whenever an electron is unpaired electron, it is called as paramagnetic in nature. So any species having unpaired electron will be called paramagnetic. What will it be called, guys? It will be called paramagnetic. Understood? Tell me, understood or not? So what we have written over here, that the ammonia solution, the ammoniated metal or ammoniated electron which is there, because of that the solution is deep blue in color and the nature is conducting. Because it is unpaired electron, it can be donated and therefore to whichever species it will donate, that species will be reduced. Am I clear? So these are all the properties. Paramagnetic in nature means what? Unpaired electron is present. Reducing means what? That unpaired electron can be donated to someone else. So the species which will accept that unpaired electron will be reduced. Now conducting. What do I mean by conducting? Because unpaired electron are present, electricity can be conducted. And what is the color of this solution? The color of this ammoniated solution is what? Blue color. Okay. That color comes because of unpaired electron. That color comes because of unpaired electron. Am I clear to everyone? Tell me. So solution in liquid ammonia, what you have to remember, it is a colored solution. It is conducting in nature, reducing in nature, and the solution is paramagnetic. And the solution is what? Paramagnetic. JEE PYQ mein they have asked questions. They've asked question on this particular topic. So very important topic. Okay, this ammoniated or the solution in liquid ammonia is very important topic from this chapter. Okay. Why this blue color is there? Because of presence of unpaired ammoniated electron. Paramagnetic again because of unpaired electron. Okay. And conducting why? Because we have ions as well as electron. No, we have ions as well as electrons. So it will conduct electricity. Now, why do we see the color? Because the color which is there, it is so the solution the solution absorbs that color which can be seen in the visible range, and therefore we get to see blue color. We get to see which color? We get to see blue color. Exactly. You know that whatever color we see actually is not the same color that we are seeing. Are you aware of this theory? तुमको ये पता है ये ऐसा सर्कल होता है system में? Yeah. So here one, two, now see. So violet, yellow, green, yellow, orange. Like that. So orange में होता है red होता है. Right. So your में से एक color orange is not there. Okay. So uh, if you are able to see green color, then actually you are seeing violet color. That is like this. So whatever color you are seeing, actually the opposite color is there. But this is what our eyes feel. Let's say this is yellow, no? Yellow है ये और ये है indigo. Okay. So this color theory, what does it say? If you are seeing yellow color, it is actually indigo colored. Or if you are seeing this yeah, blue color, then actually it is red color. Because this opposite things matter like this. Okay. So if you are able to see blue color, it is actually red color. Then if you are able to see yellow color, then it is actually indigo color, like that. This is the color theory. Are you aware of this? Hmm? नहीं ये तो कोऑर्डिनेशन चैप्टर में पढ़ोगे. You will study this in coordination chemistry. Don't worry. Okay. Anyway, moving on. Ammoniated electron done. हाँ. So on standing, the color fades due to formation of amide after liberating hydrogen gas. So NH3 when it is treated with this electron, ammoniated electron, the ammoniated cation, what do we get? We get amine. What do we get? We get metal amine. So M plus is there. This NH3 will undergo dissociation. It will form NH2 minus and H plus. That H plus will take this electron. It will become H radical. What will it become? It will become H radical. H radical with combined with another H radical, it will become H2 gas. It will become what? It will become H2 gas. Am I clear, guys? So this is the reaction. Now, very important point. Concentrated metal ammonia solution have a metallic bronze color and are diamagnetic. This line is very important. Why are they diamagnetic? Because the electrons undergo pairing. After studying for a long time, what happens? The electrons undergo pairing with each other, and hence there won't be any unpaired electron. They will be paired electrons. Therefore, unpaired electrons are called as paramagnetic, but there are no unpaired electrons, so it will be called as diamagnetic. What is it called? It is called as diamagnetic. Am I clear to everyone? Tell me. Have you understood this? And why that solution is diamagnetic? Because what happens after some time? What will happen? After some time, what will happen? When the solution is stranded for a longer time, then electrons, or not longer time, the concentrated solution is there. No. So number of electrons will be very much more. Therefore, these electrons will undergo pairing with each other. Therefore, they become diamagnetic. What do they become? They will become diamagnetic. Is that clear? Tell me. Oxo acid. Oxo acid you have studied, no? So, oxo acids are those compounds which consist of hydrogen and oxygen attached to each other. Okay. Example
So, could
S3PO4.
you show the previous slide?
This one.
Yes. Yes, sir, done.
Okay. Oxo acid you have studied already, huh? In redox chapter. Marshall's acid, Caros acid, phosphoric acid, hypophosphoric acid, metaic acid, like that. So all these acids in which oxygen is attached to hydrogen atom, such acids are called as oxo acids. Such acids are called as oxo acid. Sorry. Okay. So like it's not too much into that. If they donate H plus, what is formed? So H plus along with that, you will get a conjugate base. Example, if H2SO4 is there, it will donate H plus. H2SO4 will donate what? It will donate H plus. So H2SO4 will donate H plus plus HSO4 minus. So keep it a single arrow only. It will donate H plus HSO4 minus. So this HSO4 minus is its conjugate base. Everyone knows this, right? Moving on. Hydrolysis of carbonate. Hydrolysis of metal carbonates. So carbonates are highly stable to heat. Okay. And thermal stability order, if you see here, let me use the laser. So the thermal stability order increases down the group. Why? You have studied thermal stability while studying Fazan's rule, right? Application of Fazan's rule and all, you would have studied thermal stability in chemical bonding. Why thermal stability increases down the group? Can anyone tell me why?
Because bigger atom.
Yeah. So bigger the ion, see, polyatomic ion is there. No, carbonate is a polyatomic, it's a big ion. Is that clear? So as the size of the cation will increase, see, size of anion is fixed. When size of cation will increase, what will happen? Covalent character will decrease. What will decrease? Covalent character will decrease. Is that clear? Ionic character will increase and the electrostatic interaction will be stronger. Therefore, thermal stability will be more. Therefore, thermal stability will be more. Understood my point? Hmm? See, they have written over here. Electropositive character from increases from lithium to cesium. We all know. Therefore, stability of this carbonate salt will increase. Why? Because carbonate is a polyatomic ion. Anion. It is a huge anion. And to balance huge anion, we require huge cation as well. Therefore, down the group, the size of cation will increase. Is that clear? Therefore, we say that covalent character will decrease and ionic character will increase. And as a result, thermal stability will increase. See, thermal stability में chemical bonding में what you would have studied is that कि thermal stability down the group it will generally increase only. Yes or no? Have you studied this? It is application of all the Fazan's rule topic that is whatever you have studied. Thermal stability of metal carbonates. Tell me. No. Hmm?
Yes, sir.
Always remember down the group thermal stability of carbonate will increase. Is that clear? Why? Why is it like that? Why thermal stability is increasing? First of all, covalent character will decrease. Yes or no? So ionic character will increase, and when ionic character will increase, electrostatic force of attraction will increase. As a result, thermal stability will increase. Can we proceed? Yes, sir. The reaction. So when metal carbonates like Na2CO3 undergoes reaction with water, what do we get? We get NaOH and H2CO3. We get NaOH and H2CO3. Is that clear? Can we proceed? Now bicarbonates. See, for bicarbonates, chalo, I'll write the point. Then we'll write. Then give me so, so if generally we say in chemical bonding we don't write too much. We say that lithium carbonate is the least stable, whereas other metal carbonates are almost all the metal carbonates are highly stable. Okay, thermally they are highly stable. Okay, now coming to bicarbonates. So except lithium, okay, except lithium, other alkali metal bicarbonate exist in solid state. Exist in which state, guys? Exist in solid state. Is that clear? But lithium bicarbonate it exists in aqueous state. So this is one of the important points. Okay. LiHCO3 exists in which state, guys? Aqueous state. But other alkali metal bicarbonates like sodium bicarbonate, potassium bicarbonate, and so on, they will exist in which state? They will exist in solid state. So, okay, it's written over here. LiHC does not exist in solid form. Okay, it exists in which form? It exists in aqueous form. But other bicarbonates of metal, they exist in which form, guys? They exist in solid form. This thing is clear. Okay. And on decomposition, what are we going to get? We are going to get metal carbonates along with H2O and CO2, along with H2O and CO2. And at such a high temperature, H2O is in which form, guys? Gaseous form. It's in which form, guys? Gaseous form. इसको liquid form में मत करके आ जाना. Can we proceed? Yes. Can we proceed, guys?
Yes, sir.
So, other alkali metal bicarbonates exist in which form? Solid state. But lithium bicarbonate exists in gaseous state. Okay. Why lithium bicarbonate does not exist in solid form? Because of high polarizing power of lithium ion. Okay. And second is what? Uncomparable size of lithium ion cation and bicarbonate anion. Bicarbonate is a very huge anion. Lithium is a very small cation. So small and huge, there is a lot of size difference, right? Therefore, you can't compare them. So therefore, they don't exist in solid form. Am I clear? Moving on. Solubility in water. So solubility, now again, solubility is a factor which depends on what? Lattice enthalpy and hydration enthalpy का this thing. What do I say? On the in the there's a competition between lattice enthalpy and hydration enthalpy. Whoever will win, let's say if hydration enthalpy is more, then solubility will be more. But in this case, like for carbonates, solubility in water will be more down the road. Why? Because I told you that time, down the group, ionic character is increasing. Down the group, what is happening? Ionic character is increasing. How do I know ionic character is increasing? Because polarizing power of cation is decreasing. No, so covalent character will decrease. It means ionic character will increase. Is that clear? And when ionic character will increase, the nature will become polar. Water is polar, so polar, like dissolves like, solubility will increase. Okay, have you understood? What about solubility? So down the group, that is moving from lithium to cesium, what happens? Down the group, what happens when we move from lithium to cesium? Size increases, and when size of the cation will increase, polarizing power of cation decreases. It means covalent character decreases. It means ionic character is increasing. Which character is increasing, guys? Ionic character is increasing. Is that clear? And therefore, ionic character will increase, so solubility will increase in water. Okay? Ionic compound will be more soluble in water compared to covalent compound. Yes or no? Same is the case for bicarbonates. Same is the case for bicarbonates. We have not taken lithium bicarbonate because it exists in aqueous form. Others exist in solid form. So from sodium to cesium we have taken. Do you want to note this down, or can we proceed? Can we proceed, guys? Done, no?
Yes.
Okay. Now again, for sulfates, what is the case with sulfates? So again, solubility increases down the group. Lithium sulfate is the least soluble, cesium sulfate is the most soluble. Thermal stability also down the group increases. Is that clear? And generally it is high for all the metal sulfates. What about hydration? So Na2SO4 forms global salt when it undergoes hydration. This is important point, okay? Sodium sulfate, when it undergoes hydration with salt, it forms Glauber's salt. Glauber's salt. Okay. Also, this alkali metal sulfates, they are non-reactive towards acids. They are non-reactive toward acid. Is that clear? Why? The reason is already mentioned there. Already sulfates are formed. Already sulfate is formed. It means how we have got this sulfate. So metal would have reacted with Metal would have reacted with sulfuric acid only. No, then only we get metal sulfate. A hydrogen gas would be released. It means it is already reacted with acid. Sulfate won't react with acid because there won't be any reaction. Metal will react with H2SO4. It will form metal sulfate and hydrogen gas. Am I clear to everyone? And all this like sulfate, they all form ionic crystalline solids. What do they form? They form ionic crystalline solid. Now, if I talk about lattice enthalpy, it is highest for lithium sulfate and lowest for cesium sulfate. Highest for lithium sulfate and lowest for cesium sulfate. Am I clear? Tell me, guys. Can you proceed?
1 second.
So what would the thermal stability order be for these?
Sorry.
So the order of thermal stability.
You are asking the order of thermal stability for what?
So for sulfates,
Same. I told you the solubility will increase down the group. So therefore it is written over here. No, increases down the group. It means lithium will be least soluble and cesium will be most soluble. So
no,
ascending
so
order will be
thermal
what?
stability. So thermal stability.
Thermal sta In that case also see, thermal stability will increase with high ionic character. Okay? Thermal stability will increase with what? It will increase with high ionic character. Am I clear?
Yes, sir.
So down the group, what is happening? Thermal
So
stability will
ionic
increase
character is
down the group.
more, so it,
Ionic character is more. Yes. And
yes.
see, but not always. You have to check for bonding also. Let's say if I say this same logic is not applicable for metal hydrides. I'll explain you why. I'll explain you why. But sulfate is a huge anion. No, sulfate is a polyatomic anion. It's a huge anion. Tell me. So
Yes, sir.
therefore, for huge anion, down the group, size of cation will increase like that only. Therefore, huge anion, huge cation will favor each other. Therefore, the thermal stability will be more. But same logic can't be applied to metal hydrides, where size of hydride is fixed and like it's small compared to the size of metal, some metals. Is that clear?
Okay,
Tell me.
yes, sir.
We'll see that. Now sulfides. This is like all experimental based data. Okay, like well, you will perform qualitative analysis. At that time, you will do it on your own. But still, you can just go through it. So, what is the color of sulfide? White or yellowish solid? White or which solid? Yellowish solid. Okay. Solubility
Sir,
there.
sorry, just one line left in previous.
Sure. Array, don't worry. I'll send it to coordinator. But still, it's good if you're noting it at the same pace. It's good. No issue. But anyway,
Yes, sir,
I'll
done.
send this PPT. Then no.
Yes,
Okay. Now, sulfides में, what is the color? They are white or yellowish solids, highly soluble in water, forming alkaline solution. What do we mean by alkaline solution? Basic solution they will form. How they will form basic solution? You can see the reaction which is over there. So when metal sulfides reacts with water, what do we get? We get metal hydroxide and hydrogen sulfide gas. Now this metal sulfide which is there, if it is treated with HCl, what do we get? We get metal chloride and hydrogen sulfide gas. So when we talk about solubility in water, they are highly soluble. Why? Because the lattice will break and they will form what they will form? They will form metal hydroxides, resulting in solution becoming basic. Resulting in solution becoming basic. Okay. Again, thermal stability will generally increase down the group. Thermal stability will generally increase down the group. Okay. And what about lattice energy? Decreases down the group because lattice energy is inversely proportional to size. So down the group, size will increase. So lattice energy will decrease. Is that clear? And therefore, we say that lithium sulfide has the strongest lattice. Lithium sulfide has the strongest lattice because size is small, so lattice energy will be highest. Can we proceed?
Yes, sir.
The one who is noted.
yes.
Okay. Nitrates. Uh, Again, but nitrate में there are few points that I would like to add. Just read this. 2 minutes. 1 minute. Yeah. So for metal nitrates, actually, okay. So The nitrates are white crystalline solids. Sulfides were whitish or yellowish solid. These are white crystalline solids. Solubility again, they are highly soluble in water. Solubility increases down the group. Okay. Hygroscopic in nature, that is, they can absorb moisture from the air. Now, if you go for thermal decomposition, then it varies according to temperature. Okay. Like if you see metal nitrates, so lithium nitrate, if you see on thermal decomposition, will give us Li2O, NO2, and O2. But other metals like sodium, sodium, potassium, rubidium, cesium, on heating, they will give us metal nitrite, MnO2, and half O2 gas. Okay, O2 gas will be removed. But one point is missing. Is it there in the next slide? No, so I have to add it. So, what you have to write one more point is that NaNO3, sodium nitrate. Okay. So when you heat it on 500 degrees Celsius, okay, or when you heat it on 800 degrees Celsius, the temperature is not same, right? So the product will also be not same. So at this temperature, at such a high temperature form, NaNO2 plus half O2 gas, NaNO2 plus half O2 gas. Okay, but at 800 it forms Na2O. Only lithium. Okay, this is very important. Na2O plus Na2O solid plus N2 gas plus which gas, guys? Plus N2 gas plus O2 gas. Okay, I hope it is clear to everyone. So N2 gas and O2 gas are formed. So this is very important point from for nitrate, that sodium nitrate will have different product according to the temperature, whereas lithium nitrate will give us Li2O, but other will give us metal nitrite. Okay, and thermal stability again, it will increase down the group. So you have seen that solubility and thermal stability are till now increasing down the group, increasing down the group, increasing down the group. Yes or no? Can you proceed? Can you proceed, guys?
Yes.
Noted. Okay. Lithium nitride, only stable alkali metal nitride. Okay, this is again exceptional behavior of lithium. You will study this because no other alkali metal will form nitride. Only lithium forms nitride, and this lithium nitride further reacts with water. It undergoes hydrolysis to form lithium hydroxide, and ammonia is released. Okay, why other alkali metal do not form stable nitride? The reason is already there, because other alkali metals are larger in atomic size, therefore less attraction to nitride ion, not azide. Azide is different. N3 minus azide होता है, this is N minus 3. Therefore, low lattice energy. Okay, in alkali metals, that too especially in case of lithium. Lithium has the, like if I compare lattice energy, then it will be highest, but for other, the lattice energy is low, and therefore they can't stabilize this nitride ion. Anyway, and others undergo very slow reaction with nitrogen and go. See, these all reaction are not important. What you have to remember is that nitride, like anyway, I think it is included in the topic exceptional behavior of lithium, because lithium in this family will show exceptional behavior. Okay, आ गया anomalous behavior or exceptional behavior of lithium. Lithium belongs to group 1. Okay, laser. So lithium belongs to group 1, but some of its properties are different as compared to other elements in the group. That is why we are studying exceptional behavior of lithium. Now, what are those exceptional behavior and why they are? Because the size of the lithium atom and ion is very small, okay? And because of small size, they have high polarizing power. High polarizing power means what? They have high polarizing power, it means what? They are covalent in nature. So results in the increased covalent character of lithium compounds. Is that clear? Lithium is much harder. Melting point and boiling point are higher than other alkali metals. Okay, that is there. LiCl is deliquescent and crystallizes as a hydrate. Now, what is deliquescent? Do you know? whereas other alkali metal chloride do not form hydrates. Yes. What is deliquescent? That this deliquescent and hygroscopic, are they related to each other? Tell me. Yes, guys, tell me. बच्चों बोलो क्या बोल रहा हूँ मैं. Are you guys there or not? What does deliquescent का मतलब क्या है? कुछ नहीं. ये क्या करता है? Like
Where it
it will also.
dissolves in the moisture, it absorbs.
So it will also absorb the moisture from there, but the extent of absorption of moisture is very high. It's that high that the compound absorbs so much moisture that it gets dissolved. It gets dissolved in that like H2O from the moisture, and it will form a solution. Is that clear? So LiCl is deliquescent and crystallizes as a hydrate. LiCl dot 2H2. Okay. Whereas other alkali metals, chloride, do not form hydrates. They won't form hydrate. Lithium is the least reactive but is the strongest reducing agent. Lithium is the least reactive but is the strongest reducing agent. This reducing agent, strongest reducing agent, is in which medium? Aqueous or gaseous medium?
Aqueous.
Aqueous medium.
Aqueous.
Gaseous medium, it is the least one, na? It is the least reducing strength. Who is the highest reducing in gaseous medium for group 1?
Cesium.
Cesium.
Cesium. Very good. Okay. And combustion in air. So when it reacts with oxygen, it forms uh, oxide, and with nitrogen, it will form nitride. We have studied no that lithium reacts with oxygen, it forms lithium oxide. Sodium forms peroxide, but other elements of the group forms superoxide. Okay. And then lithium hydrogen carbonate is not obtained in the solid form that we have already studied. It exists in which form? Aqueous form. All other elements form solid hydrogen carbonate, that is also we have studied. Lithium forms no ethanide on reaction with ethyne. Other alkali metals form ethynide on reaction with ethyne. What is this? Have you understood this? क्या है ये? Ethynide. Why lithium? अच्छा ethynide क्या हो जाएगा? Ethyne तो सुना है सर हमने. Ethyne is 3 member rings. What is ethynide? अरे ethynide ion होगा ना? What is ethynide? Cyanide will be what? It will be ion. Yes or no? बोलो.
Yes, sir.
But कौन सा ion?
Uh,
जो
HC triple
जब
bond
अपना
C minus.
HC
One
triple
H,
bond
H will
C
go.
minus. One H
One
will
H
only
will.
go.
Both H will.
हाँ. पहले एक
Oh,
जाएगा फिर दूसरा भी जाएगा. Is that
oh.
clear?
So be 2
Very good.
minus.
हाँ. Pahले, like one by one basicity, no. So first it will lose one H plus, then it will lose one more H plus. Okay. चलो. So, but why is it lithium forms no ethanide on reaction with ethyne? Why? Because lithium क्या है? Lithium is reducing agent. No, it will donate electron. Ethynide is already electron rich. Ethynide is already electron rich. समझ में आ रही मेरी बात? ये जो इथाइनाइड है, इट इज व्हाट? Hc ट्रिपल बॉन्ड C माइनस और C2 माइनस. मतलब when it loses both the H plus. So they are already electron rich species. Lithium donates electron to others because it is very good reducing agent. But will it donate electron to already electron rich species? The answer is no. Is that clear? Therefore, lithium won't form ethynide. ठीक है चलो. This we'll see when we can do. It's already 2 o'clock. Or shall we complete the anomalous behavior of lithium? Hmm? Only one point is remaining. चलिए बोल लेते हैं. Lithium nitrate when heated gives lithium oxide. That too we have studied, like we saw already. And same case is there for sodium nitrate as well, but at 800 degree temperature. Sodium nitrate will also give same kind of product, sodium oxide and NO2 gas and O2 gas, but at what temperature? At what temperature, guys? At 800 degrees Celsius. Okay. But other alkali metals gives nitrate, sodium nitrite on. Battery is low. Everything is saying कि बस हो गया in the class. ठीक है. Done. And the last point is what? lithium fluoride and lithium oxide are comparatively much less soluble in water than the corresponding compounds of other alkali metal. Why? Because they are covalent. Because they are covalent. Lithium oxide and lithium fluoride are covalent in nature. That's it for today's class. Okay? Just a minute. Let me check the attendance. Okay. ठीक है. You can leave the news. Bye bye.
Thank you, sir. Bye, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.